Welcome, one and all, to the Cool Worlds podcast with me, your host, David Kipping. This episode, I am joined by Will Kinney. He's a professor of physics at the University of Buffalo. And I guess the key point for this episode is he is an expert on the topic of inflation. So he's a physical cosmologist. He studies the origins of the universe, dark energy, dark matter, topics like this. But I guess the thing that he has had the greatest impact in terms of my perception, is in terms of trying to explain this very difficult, impenetrable topic of inflation. Now, if you have any interest in the origin of the universe and you've seen any videos about the Big Bang or anything like this, then you have probably at some point encountered this word inflation, this period in the early history of the universe where it seemed to have expanded extremely rapidly. So, doubling at least 80 times in size in a very, very brief period of time, fractions of a second. And that rapid expansion is ultimately what gives us the universe that we see today. Right? So if you didn't have this, then essentially we wouldn't have any of the structure, wouldn't have any of the matter content, we wouldn't have the energy content of our own universe. All of that is really driven by this period of inflation. So it's a very, very critical period to understand. It has also an enormous amount of evidence supporting it. This is not one of those pie in the sky ideas. Like, I don't want to pour cold water over string theory, but string theory, for all of its mathematical elegance, is struggling to be able to make sort of a convincing experimental evidences to say, okay, this is clearly true because we have a series of predictions that this theory makes, and boom, 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 we've got them lined up. But inflation does that. So I think a lot of people don't appreciate that. I think people think inflation is this ad hoc arbitrary theory with no grounding evidence, but that is not true. So Will has done the wonderful job of trying to explain this to you, to me, to the whole world in this wonderful book, An Infinity of Worlds: Cosmic Inflation and the Beginning of the Universe. And this is a book that we desperately needed, because there just is really to use the paraphrase, there is a black hole of information, if you like, about the term of inflation. There is not a lot of great books out there which really explain this. And Will has done the hard work of trying to take this very technical topic, very abstract topic of inflation, and trying to explain it with these beautiful analogies, everything from beer to balls rolling down hills, all this kind of stuff. So some wonderful analogies that you'll be able to get your head around. I'm going to dive into those in today's conversation. So in this chat, what we're going to do is we're going to try and walk through the idea of inflation, what it is, where it comes from. We're going to walk through some of the evidence that we have that supports this idea. And finally, we'll get into some of the mind-bending consequences that inflation truly implies. So I hope you enjoyed this one. And as always, I'll see you at the back end. Well, it's such a pleasure to have you here today.
Thanks. I'm really happy to be here. Thanks for inviting me down.
This book that you've written here, The Infinity of Worlds, it is a book that I've been waiting for a long time, because inflation is a very challenging topic, yet one which there isn't a lot of books about. So was that one of your reasons for tackling this?
Yeah, and it's really become one of the foundational ingredients to what we think of as a standard model of cosmology now. So you have, the lambda CDM is sort of the late time picture of the universe, right? So we have a cosmological constant, we have dark matter, all of these ingredients come together to make this very successful model of the universe. But underlying that, the sort of the bedrock on which that entire picture rests is really this idea of inflation in the early universe. So it's a key piece of our current understanding of cosmology.
It's a bedrock, and it's a bedrock that we don't often. When I took cosmology, it's not something we had like one lecture on it. It was very brief. It doesn't get enough attention, I don't think.
Yeah, and so in particular, there's not a whole lot of popular treatments of it. Nothing really since Guth's book in the early 1990s, and a lot has happened since then.
We're going to get into all of that. We're going to get into all that today. So we're going to have a whole discussion today all about the joys of inflation. And I thought, just to get us started, we need to get everyone on the same page. We need some clean definitions. You talk about the universe a few times in the book, or many times in the book, the universe. And the universe can mean different things to different people. So it could mean the furthest distance to which we can see. the particle horizon, if you like, the Hubble volume, or it could be the infinite potential universe that lives beyond that, or it could maybe people when they say universe, because universe technically means everything, it could maybe mean the things outside, like the other universes as well. Like what's your definition of universe?
Yeah, I mean, so there are many overloaded words that that you come across when you talk about this stuff, like universe and what do you mean by the Big Bang and so on. So what I mean, sort of the working definition of what I mean by the word here is the entire infinite space that we live in, or potentially infinite anyway. Right. So we have an observable universe that is about 40 billion light years in radius, which is as far out as we can see. But we know that the space is bigger than that. Right.
How do we know that from how?
One of the ways you can think of it is by measuring the curvature of the space, and we'll get back to talking about flatness. But basically, if you could put a bound on the curvature, you can put a bound on sort of the total, the amount of physical volume that exists outside the universe as well. So that if you measure the curvature to be small enough, that tells you that there's almost certainly the space extends beyond the observable universe.
Okay, so I guess it's like if you're on the Earth and you measured the curvature of the
Exactly,
surface of the
right.
Earth.
And so you can tell, you put a lower bound on how big the Earth is by how far out you have to look to see, the horizon or something like that, right? I mean, so arguments like that can tell you that the universe is almost certainly larger than what we see. There have been some work on looking at closed topologies as well. So you can have flat universes that you turn into a torus.
Yeah.
And if that torus were small enough, you would start to see multiple images of things, for example, in the cosmic microwave background, because you would see more than once around the universe. Yeah. And so you can put a lower bound on how big that compactification scale is by, for example, observing large-scale structure in the cosmic microwave background. And that scale has to be considerably larger than the observable universe that we see.
I'm really glad you mentioned that because one of my videos that did really well on the Cool Worlds channel was about the different compactifications, and had some help from Jana on that, who's written about this quite a few times. And the torus is a strange idea, but it does make sense that it's flat. I think the easiest one to imagine is the 2-cylinder or the 3-cylinder. Like take a sheet of paper and roll the two sides together.
You don't have to stretch it.
Yeah, you don't have to distort any, so you can still draw your triangles. You can still have those Euclidean 180-degree triangles, which is really what we're measuring, I think, when we do these cosmological observations. And if you could wrap the two ends together, which does require a little bit of distortion, then you could get a torus. But it was actually John Nash who proved there was a way of doing that by putting in these little creases all alongside. And you can, if you put in just the creases in the right way, you can actually create still this flat fundamental domain. I think it's usually language we use.
An example that people are probably really familiar with is a video game screen like Asteroids.
Yeah.
Right, the old video game where you go off one side of the screen, you just come back on the other. So all they're doing is they're identifying the sides of the tops and the bottoms. Topologically, that is a torus. And you could compactify the entire universe in that way if you wanted, except that scale has to be bigger than the observable universe by quite a bit.
So we'll get obviously into inflation a lot more depth later, but maybe just think this is a very quick question whilst we're on this topic. Does inflation require or suppose a true infinite plane, or does it work also if you had one of these toruses or cylinder type configurations?
You can initiate inflation in a compact region. There are bounds on that. It's harder to do than you might think. There's some really interesting papers on the conditions that are necessary to sort of nucleate an inflationary space within some pre-inflationary universe. But you can also do it in a compact region. And for example, there's a models of inflation called topological inflation, where you actually have these topologically closed structures that allow you to initiate inflation within them. So there are a lot of ways you could do it, and inflation does not necessarily assume an initially infinite universe, although it certainly works quite well if there is that.
Okay, so before we get into inflation, because we're kind of teasing it already, we're going to talk about the CMB quite a few times. So I think that's another good thing to ground us on. Tell us what exactly is the CMB and what do we measure from it?
Okay, so the early universe was very hot and dense. Right, so the universe today is expanding. If you turn the clock around backwards, everything gets crunched together. And if you take a whole lot of hydrogen gas and crunch it together, it gets hot. And so the very early universe, we believe, was in a high degree of thermal equilibrium. It was mostly dominated by, there was only hydrogen and helium at the time. These were pretty much the only things that were created in the early Big Bang. So you have this very hot, very smooth, very dense soup of hydrogen and helium gas. And when it's hot enough, that all that gas is ionized. All the electrons are stripped off of it. So you have this big plasma of hydrogen nuclei, helium nuclei, and a bunch of free electrons that are just streaming all over the place. And also, and it's in thermal equilibrium with a background of photons, so a black body spectrum, right? So it's a completely equilibrium system. Those photons are scattering rapidly because the free electrons interact strongly with the photons. So the light interacts strongly with the material, and so it would have been like an opaque cloud, like you're in a fog. You can't see very far in front of you, because of the fact that the light is scattering so rapidly off the free electrons.
If you turn your fog lights on in a fog, it doesn't really help you.
That's right. You just see nothing, right? But then the universe, as it expanded, cooled. And when it cooled below about 3,000 Kelvin, which happened about 380,000 years after the Big Bang, the temperature of the universe got low enough that very rapidly all those electrons got captured in the nuclei, and the universe went from being an ionized plasma to being neutral hydrogen and helium. And the rate at which photons scatter off neutral atoms is much lower than off free electrons. And so what happens is the universe very quickly becomes transparent. But there's all this radiation left, this black body, and the best black body ever measured. One of my favorite facts about the FIRAS instrument on COBE that actually measured the black body of the cosmic microwave background, it's still the best measurement out there almost 30 years later, was that the CMB is a better black body than the reference black body they had on the satellite to measure it. And they had to do all kinds of cool experimental tricks in order to...
Just because like atomic, I guess, like slight deviations in the material.
I mean, making a black body as good as the CMB is almost impossible.
Yeah. Wow.
But all that light was left over and just started streaming in all directions. And basically, there's this leftover gas that has gradually been cooling. So it started out at 3,000 Kelvin. If you were there at the time, the universe would have been kind of glowing a soft red. It would have been actually in the visible wavelengths, visible and infrared. Mm-hmm. You would have been able to see it with your eye.
But no structures at this point. It was just
completely smooth, right? Yeah. And then as the universe cools down, now it's because the universe has expanded by about a factor of 1,100 between then and now, that 3,000 Kelvin black body is now a 2.7 Kelvin black body, and it's mostly in the microwave. So, for example, if you take an old school television like a UHF or VHF television and tune it to just static, about 1% of that static is actually photons left over from the Big Bang. You can just see it yourself in a television.
Yeah, at least the old televisions.
Yeah, the old ones, not the digital ones. Yeah.
So that's kind of fun. So this is one of the most powerful windows we have into cosmological models. Is a way of testing them. It seems like this is our primary tool in investigating the universe.
It's especially important for constraining inflation models. And the real power of it is the universe back then was very simple. There was no structure to speak of. There was no heavy elements. There was no dust. It was an incredibly simple symmetric system. And so we're really looking, when we look at these photons, we're looking at light that has traveled directly to us from when the universe was a little under 400,000 years old, right? This is something that I like to say when I talk about this, is that looking out in space is looking back in time.
Yeah.
The further out in space you look, the further back in time you see. And when we look at the cosmic microwave background, that is the oldest light in the universe. And we are really observing what the universe looked like at an age of a little under 400,000 years. The cosmologists are lucky, unlike archaeologists who have to piece together the past from bones and make inferences based on sort of decayed relics. We can actually just go out and look and see what the universe looked like at these very early times, because we just look out and look into the sky and see it directly.
So it comes in from all directions, this radiation, which obviously tells us that we're not in a special position. We're just this is kind of the cosmological principle, essentially. Right. The universe appears, is it isotropic and homogeneous? That's the definition, I think, of this cosmological principle.
That's correct, yeah. Okay. So homogeneous means the same at every point, and isotropic means the same in every direction.
Yeah. So in principle, could you measure, this is the earliest thing we can detect right now, because it's electromagnetic radiation, but there's other multi-messenger astronomy that we're trying to do.
So there's also believed to be a neutrino background that has slightly lower temperature than the photons. It's about 1 Kelvin. for various reasons. But these neutrinos, it's because the neutrinos decoupled from the background earlier. So the universe became transparent to neutrinos much earlier than it became transparent to photons.
Then why wouldn't the neutrinos be hotter?
Because of the fact that the neutrinos decoupled before electrons and positrons annihilated. So the electrons and positrons the temperature was high enough that you're creating matter and antimatter, electrons and the antimatter version of the electron called the positron. These are being pair produced rapidly. And then when the universe cools below the electron mass, they all annihilate each other and you only have the electrons left over because there's a little bit more regular matter in the universe than antimatter. That happened after the universe became transparent to neutrinos. And so the heat that was produced by those electron-positron annihilations heated the photons but didn't heat the neutrinos, so they're cooler.
I see. So if we did one day detect the cosmic neutrino background, it's not going to be 380,000 years since the Big Bang. How far back would that be?
I'm trying to remember the number. I think it'd be something in the neighborhood of about 50, 60,000.
And another probe might be gravitational waves. We'll probably talk about that.
Gravitational waves, in principle, you could see all the way back. In particular, inflation predicts the production of primordial gravitational waves. And so if you could detect that background of gravitational waves, you would actually be directly observing basically gravitons that were emitted before the hot Big Bang itself.
Wow, that'd be awesome.
Which is just mind-blowing, yeah. And there are serious efforts underway to detect that background.
Okay, so that's good to know. So the CMB is not the be-all and end-all. There are still at least two major new frontiers right there that we've already talked about.
Other particles that stop scattering earlier.
Yeah. Okay, so we've talked about the CMB. So let's talk about a couple of problems in cosmology, and two in particular. Well, I think there's really three problems which really motivate inflation. I'm thinking of the magnetic monopole was sort of historically.
That was Guth's original motive, yeah. It's become sort of an antique idea.
Right, we'll get into that a little bit later, so why people don't care about that one so much. But the other two are the horizon problem and the flatness problem. So maybe we can start with the horizon problem and explain to us what exactly that is and why it's a problem.
Well, the horizon of the universe is, we've already mentioned this, is as far out as we can see. And the reason that we can only see out a finite distance is because the universe has a finite age. Remember, looking out in space is looking back in time. So the further out we look, the further back in time we see. Well, the universe is only about 13.8 billion years old. Remarkably enough, we have that measured to within an error of a couple of 100 million years. And so if we look out essentially 13.8 billion light years, you factor in some expansion effects, that turns into about 40 billion. That you pick any direction in the sky, if you look out that far, what you will actually see the Big Bang itself. And there isn't anything past that because the Big Bang hadn't happened before that, right? And so this is called a horizon. Basically, it's the speed of light times the age of the universe with an order unity factor from expansion out in front of it. And that tells us that if the universe is 13.8 billion years old, you can only see out 13.8 billion light years and you run out of universe. And this is called a horizon.
It's really a time horizon in that sense.
Yeah. Well, time and space end up being sort of different sides of the same coin at this point. You express it typically as a distance, though. And we've already talked about the fact that the universe is almost certainly bigger than that, but we can only see this little bubble of it, just like you can only see a certain fraction of the Earth. You know, if you're out at sea, you can see out about 12 miles or so, and then the Earth curves away from you. So it's similar to the horizon on the Earth in the sense that the curvature of the Earth only shows you a finite patch of this larger space. That horizon gets bigger with time, right? So when the universe was 1 billion years old, it was only 1 billion light years out.
Right.
When the universe was 100,000 years old, it was only 100,000 light years
modulo
across.
Some expansion.
Yeah, I mean, there's an interval you have to do there, but that doesn't change the physics.
Yeah, but ballparking it, yeah.
And so if you work it out, if I look at the cosmic microwave background, that light was coming to me when the universe was only 400,000 years old. So the observable universe at that time would have been only 400,000 light years, give or take. And if you map that out to how big that would appear on the sky, it's only about a degree across, about twice as big as the full moon. So if I look at a photon coming at me from the cosmic microwave background, when that guy was emitted, his observable universe is only a few 100,000 light years across, only about a degree on the sky. And nonetheless, if I look at it in a different direction on the sky, that photon's horizon was only about a degree across. Yet this point and this point were in thermal equilibrium to a part in 100,000. Remember, the best black body ever measured in nature
So they're the
And-
same temperature,
Yeah.
which is spooky.
Except they had never even been remotely close to being in causal contact.
Yeah.
Right. These guys can't see each other. So how did they know to be at the same temperature? And so the fact that the universe is smooth on scales that are bigger than the observable universe, especially at early times, we can measure this in the CMB, is unexplained in sort of the standard Big Bang cosmology of like the 1970s. You know, there was just no explanation for why the universe would have started out so in such a high degree of equilibrium on scales that were separated by such distances that they didn't have time to talk to each other in the amount of time they had since the Big Bang. So that's called the horizon problem. Why is the universe so smooth on scales that are bigger than the size of the observable universe?
Yeah. So as the universe gets older, the horizon is growing.
Yes.
So we're seeing new parts of
that's actually not happening anymore, but we could talk about that because of dark energy. But
yeah, that's true. But in principle, this was sort
for
of
most of the history.
for most of the universe, this was true. And as that expands, you're sort of seeing more and more and more of the universe. And I guess as an observer, you would be like, "Huh, isn't that weird? Even though I just saw this new part of the universe over here,
it's exactly the same as this other part.
It's exactly the same as that guy. Even though there's no way they could have possibly communicated with each other."
Exactly.
That's very spooky.
And one of the things that inflation does is provide a causal mechanism for explaining that kind of homogeneity.
So could you get around it? Because this is all sort of embedded this idea of a finite causal speed, which is the speed of light. Could you get around it by changing c in some way?
Absolutely. And there have been various attempts to do that. João Miguel is a guy who has done a lot of work on, and also Andy Albrecht, who have done some really neat work on varying speed of light theories. And I've
And
actually
what does that look like exactly? It's like a rapid slowdown of the speed.
Yeah,
of
so you
something?
start out with the speed of light really big, and then it gets smaller with time. And so the
Okay.
things start out, they can talk to each other because the speed of light is really huge. And then the speed of light drops down to its current value and gives this apparent lack of causal connection between these things that were actually causally connected. I've worked on theories where you actually have the universe is full of a fluid that has a speed of sound faster than the speed of light. And you can pull similar tricks with that.
Okay, but these are generally not favored because there's no, I guess, real motivation for proposing them, nor do they solve the other problems. They just solve that one aspect.
Yeah. And remarkably enough, you can actually make these consistent with relativity. These theories that have superluminal communication, there's a loophole in relativity that nothing can travel faster than light in vacuum, but things can travel faster than light in a medium. And you don't run afoul of the limits on light speed in this way.
So you have like an ether almost.
Yeah, that's a superluminal ether.
Yeah.
And because of its properties under Lorentz transformations, it doesn't violate relativity. It's a really cool loophole.
Okay. So we could talk more about that, but I want to move on to the next problem because there's a whole bunch of problems to deal with, and the next big one is the flatness problem. We kind of talked about this a little bit already, but we see a very flat universe around us in terms of this curvature. How do we measure that, and why is it a problem?
This is spatial geometry, right? So, like the surface of this table is flat, which means that if I draw a triangle on it and measure the angles on that triangle, they'll add up to 180 degrees. Now, if I took a globe and drew a triangle on that and measured the angles on it, because of the fact that the surface of that globe is curved, those angles would add up to more than 180 degrees. Or if I took a saddle from a horse and drew a triangle on that, because of the curvature of that saddle, those angles would add up to less than 180 degrees. Same thing with the universe, right? Solutions to the Einstein field equation for cosmology, if I say, okay, I want to have a homogeneous isotropic space, it turns out that there are three classes of solutions that satisfy Einstein's equations. And you have positive curvature, negative curvature, and flat geometry. And it's determined by the density. So if the density is greater than a certain critical density, which in the universe today, the critical density is about the mass of 5 hydrogen atoms per cubic meter.
What do you mean by critical? Just define that one more time.
So the critical density is, if the density of the universe is bigger than this, it has a positive curvature. If it's less than that density, it has a negative curvature. And if it's exactly that density, it's flat.
So this is just the gravitational influence of that density of material.
Exactly.
The
curvature is created by the matter inside the space.
Okay.
And what curvature you have depends on how dense the matter is. And it turns out that the universe is exactly balanced on that razor's edge of the critical density. And we can measure this by making a really big triangle and measuring its angles. And the way we do this is with the cosmic microwave background. Remember I said that the size of the observable universe on the CMB was about a degree across? Well, you can calculate that. You can say, I know how old the universe was, I know what the contents of this plasma were, and so on, and I can figure out how big the horizon size of the universe would have been at that time. And you can see that horizon size in the little fluctuations in the cosmic microwave background. They have a characteristic size that's determined by the causal length, by the size of the observable universe. So you can measure it. Depending on the geometry of the universe, the apparent size of that on the sky will change. So if the universe is positively curved, that thing will appear bigger on the sky. If the universe is negatively curved, it will look smaller. And if it's exactly critical, then it will be about a degree across. Basically, you're making a triangle where one side of the triangle is on the cosmic microwave background and the other two legs are your line of sight.
It's like a magnifying glass or almost the inverse.
Yeah. And so this has been done with cosmic microwave background measurements, and the universe is flat to within, it's now a sub% measurement. It's just incredible that we can measure the curvature of the universe to around 0.1% or so.
And why is that a problem?
Because it's an unstable equilibrium. This is an example, if you like, of we're probably going to talk more about fine-tuning problems, but this is highly fine-tuned in that if I start out in the very early universe with even a tiny little deviation in curvature from flatness, that tends to amplify. So if the universe is a little bit closed, then it gets more closed. And so if I say, okay, the universe is flat to within 0.1% today, if I go back to the cosmic microwave background, that curvature had to be apart in a few 100,000. And if I go back to like primordial nucleosynthesis or some of these early stages in the universe, then it had to be flat to like 1 part in a trillion.
So we're balanced on the pinhead almost.
Exactly.
At this point, yeah.
And there's no dynamical explanation for that in a standard Big Bang cosmology.
Is there an anthropic reason you could justify why the universe has to be this way, else we couldn't be alive and we couldn't be here?
Well, yeah, I suppose. I mean, if you just like sort of if you just rolled the dice and created, some sort of like expanding universe, you would tend to expect the curvature would be of the same order as, that the universe would basically, the characteristic lifetime of a universe that you picked at random would be about the Planck time, about 10 to the minus 33 seconds. So another way of stating the horizon problem is, why is the universe so old? Typical lifespan should be a tiny fraction of a second, but here we are 14 billion years later and everything's just great, right?
That's true for both positive and negative curvatures, or just...
Positive curvature, it would recollapse on itself. Yeah. Negative curvature, it would just empty out.
Yeah, so that's like the extreme dark energy type situation.
But the easiest way to think of it is if you nucleated it with a small positive curvature, it would tend to just recollapse on itself in about a Planck time, about 10 to the minus 33 seconds. And that would be sort of naively what you would expect if you threw the numbers into the theory.
Okay, so we have the first problem, the horizon problem, is that there's parts of the universe which seem to know about each other, even though they're greater than the speed of light modulo their age distance, so that shouldn't happen. With the flatness problem, that we seem very finely tuned in terms of...
In an unstable equilibrium.
Yeah.
If you push it a little bit, it falls off.
Or a metastable?
It's not even metastable in matter radiation dominated cosmology. It's just unstable. It just grows. Yeah.
Okay. And then finally, we have this magnetic monopole problem that we alluded to, that was the original inspiration.
Right. So back in the 1980s, when Guth was formulated, Alan Guth, people were working on what were called grand unified theories. These were models of unifying essentially we understand how electricity and magnetism unify into a single force, the electromagnetic force. That was figured out by Maxwell in the 1800s. And then in the 1970s, that electromagnetic force was unified with the weak nuclear force by Steven Weinberg's theory. And that's called now the electroweak force. Right, so we realize that all three of those four fundamental forces are just different aspects of the same thing. And with the discovery of the Higgs boson, this was vindicated, right? The Higgs is the thing that does this unification. Well, motivated by this, people said, well, what about the strong nuclear force? We could maybe unify all of those fundamental forces, electromagnetic, weak, and strong nuclear force together, and this is called the grand unified theory.
But not gravity. We're leaving gravity out.
Gravity is like the next step. So that would be where you're talking about what's called the theory of everything, with unified gravity with the other forces. But this was a more modest problem where they're just trying to look at the electroweak force and the strong nuclear force. And one of the problems you run into there is that generically, when you allow those forces when you think of those forces as aspects of the same thing, you start making magnetic monopoles. So magnets that only have a north or a south pole. And in fact,
which we don't see in nature.
Right, which we've never seen. But when you work out in these theories, they would be copiously produced in the early universe, and the universe would just be completely full of magnetic monopoles.
So they would kind of act like a positive charge and a negative charge, like a proton and a
like an electron has a negative charge, or a proton has a positive charge. And if you stick them together, you get a dipole, right? You have opposite charges. Magnets only come in dipoles, as far as we know. And so, but these theories, almost all of them necessarily predicted that there would be large numbers of magnetic monopoles that would be produced in the early universe, and we don't see them. So the question was why? And inflation was a way for Guth to essentially dilute away all of these magnetic monopoles that were produced in the universe and give us a universe that we could see. And it was then he realized that, it solves all of these other problems too, but at least from the way I've heard the history told, that there was a monopole problem that he was really concerned with when he came up with the idea of inflation.
So the other kind of, I don't know if this is really a data point, but it's certainly, you kind of allude to it as almost a constraint in your book, and that there is a beginning or a singularity to the universe as well. So quoting from your book, you said, if we apply Einstein's general theory of relativity to a homogeneous isotropic universe, we find that such a universe must inevitably evolve. We also find that such a universe must have had a beginning, a boundary in time beyond which neither time nor space exists. So the contention is that there is a start, and this is a general, you can't really imagine general relativity without that happening.
This is, one of the funny things about Einstein's general theory of relativity is, in many ways, it contains the seeds of its own demise. And these come about by these things called singularity theorems. And this is, for example, it was Roger Penrose was very famous for proving some of these very early theorems about singularities and relativity. Basically, in Penrose's singularity theorems, we're talking about the centers of black holes. And he found that once you got stuff trapped inside a black hole, there was nothing that could stop it from collapsing down to essentially a point. And then everything blows up and you don't know what happens.
How do you define a singularity in that context exactly?
In this case, it's a point where the curvature of the space-time becomes infinite. Okay. Right. So, and if you think about like all these particles falling into the center of a black hole, they all come together at a point. And so the density of the matter that falls into the black hole becomes infinite. And in fact, it's just sort of nobody knows what happens, right? The inflation, the cosmological singularity is of a different nature. So it's not a point, it's actually a surface. One way to think of that is the way I like to describe expansion of the universe is a two-dimensional analogy. Imagine you have a big rubber sheet, right? And you draw squares on that rubber sheet. They're all identical, so the space is homogeneous and isotropic, right? It's the same at every point. But you can stretch that sheet and those squares will get bigger and bigger and bigger and bigger. Now imagine that sheet going off infinitely in every direction. So you can have an infinite geometrically flat space that's expanding. It's not expanding into anything, it's expanding into itself. But those squares on that surface are getting bigger and bigger. If you turn that back around, go back in time, those squares get smaller and smaller. And if you solve Einstein's field equations, for example, for a universe that's dominated by dark matter or dominated by photons or any normal sort of stuff, that evolution is a power law, and it goes basically, you solve Einstein's equations and those squares go to zero size at finite time in the past. So the singularity, the Big Bang, happens everywhere in an infinite space at once, where all of these squares on this infinite grid go to zero size at finite past time, and the universe gets an infinite density. So the Big Bang is an infinite, hot, dense, homogeneous universe popping into existence all at once.
Yeah, and it's not a point. It's infinite.
It's a boundary in time, right?
Yeah, but I think a lot of people, who aren't astronomers and cosmologists, tend to imagine there is like a location somewhere in the universe where the Big Bang happened.
Like an explosion and everything flew out away from it.
The tourist hotspot. We all go there one day, but this is where the Big Bang happened. But that's
no, but in fact, so if we sit here and we look out, the further out in time we look, the further out in space we look, the further back in time we see. The Big Bang is actually, from our point of view, a sphere with us at the center. So it's actually a remarkably sort of Aristotelian universe that we end up with, where we actually are at the center of the universe, and the outer edge of it, that the sphere that separates us from the Empyrean realm is actually the Big Bang, right? And we sit at the center of that.
And in fact, every
observer in the universe sees himself at the center of their own universe. That's right. Yeah.
Which is also true of a lot of social media and stuff as well.
But those singularities, in a standard Big Bang cosmology, those singularities happen at finite past time. You can calculate. And that, when we say the universe is 13.8 billion years old, that's what we mean, is that zero time point that we infer from our current expansion happened that long ago.
So that's almost kind of a problem, because I think if you ask, go to a school and you talk about cosmology, the question you inevitably get is, what caused the Big Bang? Why was there a Big Bang? And this is another kind of problem that I think inflation touches on.
The universe in inflation can be vastly older than that 13.8 billion years, because that moment where the hot, dense equilibrium universe came into being 13.8 billion years ago, in inflationary theories, is actually the end of inflation.
We'll be right back after this short message. This episode is brought to you by our sponsor, NordVPN, my personal VPN of choice for the last few years now. So I'm sure you know this already, but VPNs add a vital extra layer of protection when you're online, redirecting traffic through proxies which mask your IP address. Especially when you're using public Wi-Fi's like at coffee shops and airports, this has become an essential tool for me and my family. NordVPN has over 5,800 servers in over 60 countries worldwide, so you can make it look like you're just about anywhere. So a neat side benefit of this is that you can actually stream TV shows that are only available in certain regions. And trust me, NordVPN is plenty fast enough for this. I love it because the app is clean and simple, and it works on everything from your phone to your smart TV. So we've partnered with NordVPN to give you the best deal out there. When you use my link, you will get a huge discount on their 2-year plan, plus 4 additional bonus months. So get it at nordvpn.com/coolworldspodcast. It's risk-free with Nord's 30-day money-back guarantee, and it is the best deal on the internet. Once again, that's nordvpn.com/coolworldspodcast, or click the link in the show notes. Now back to the episode. So let's do it then. Let's we've kind of been dancing around inflation, but let's fully attack it now. Maybe we'll get back to the original idea, like Alan Guth's original work. What was the premise of inflation? What was the idea? What was it proposing for the nature of the universe?
Guth's idea, you mean?
Alan Guth's idea.
Yeah. Well, he used an analogy from condensed matter physics, which was supercooling. Right. So the idea that you can have, for example, a supercooled fluid, where basically if you take a very pure water and cool it down very slowly and carefully, you can actually cool it down below its freezing point without it freezing. And then if you disturb it in any way, it'll all just go freeze. So it's called a metastable equilibrium. Something that a superheated fluid is something you see when you make coffee in the microwave a lot. You ever heat up a cup of water in the microwave and then you toss in a stir and it bursts into a boil?
Yeah.
That water is superheated. It's in a metastable equilibrium, and you disturb it and it falls off that.
So it has a phase transition.
Exactly. A sudden phase transition that happens. And Guth's original idea of inflation was that the universe was in this sort of essentially like a superheated state, where or a supercooled state, where the universe had expanded and cooled down, and there was a phase transition that was delayed, like this cold water that was not allowed to freeze. And that delayed phase transition, he worked out, would actually cause the universe to expand exponentially quickly. So it would create this super fast expansion. And this is how you get rid of the monopoles, is that super fast expansion then dilutes away all the monopoles and you're good. Right?
But there isn't actually a fluid here.
Well, the fluid here is a particle. And in these theories, it would be the analog of the Higgs boson, except the one that is used in these grand unified theories. So it would be a field like the Higgs boson that would be causing this. So basically you would have a supercooled Higgs field that would be driving this.
And then this undergoes some kind of phase transition.
Right, and then that ends inflation and gives you a hot Big Bang. So the universe during the inflationary period, during the supercooled phase, would be entirely empty at essentially absolute zero temperature. There would be nothing in it except this Higgs boson stuck in this metastable equilibrium. Everything else would get diluted away. The monopoles, the atoms, everything gets diluted. The universe ends up completely empty, absolute zero temperature. And then this supercooled phase suddenly ends and heats the universe back up.
So maybe one way for me to describe it here, and tell me whether this is right or wrong. There is a universe or state before our current phase where everything is expanding mind-bogglingly fast away from each other, and this is the state of inflation.
Yeah.
And then that is not a completely stable state, and it's almost teetering on the edge of always dropping to a lower state. It does that phase transition, and during that phase transition it liberates a huge amount of conventional energy.
Like that teacup with the hot water, when you toss the stirrer into it, goes bursts into bubbles. And this is what happened in Guth's conception of it, was what happened at the end of inflation. This didn't work, however, and the reason it didn't work was because those bubbles that you make in that phase transition, the universe is expanding so quickly that those bubbles are being stretched apart from each other faster than the speed of light, and they can never
what are the
percolate.
Bubbles here?
So these are the bubbles of the true vacuum, right? So the phase transition doesn't happen uniformly; it happens in these little bubbles. So you get these little bubbles of
in which we live. We live in one of those bubbles,
right? Except that those bubbles never have a chance to run into each other, and that was how the mechanism he wanted to use to heat the universe was these bubbles bumping into each other would cause particle production and create a hot Big Bang.
Oh, so I think I misunderstood that then, because I thought it was the phase transition from this homogeneous fluid, whatever you want to call it, this inflaton field, decays into a bubble, and that nucleation process itself generates the energy. But it sounds like here you're describing
that's the more modern concept. So Guth's idea was bubble collisions that did the heating, that didn't work because he couldn't get the bubbles to collide fast enough.
Okay.
So now. And so he realized this, and if you read his original paper on it, he knew that at the time. He said, I already know this doesn't work, but we'll try to fix it up later, right? And they did fix it up. So, and this was Andre Linde, and at the same time, Paul Steinhardt and Andreas Albrecht realized a way that they could do it.
And when was this?
This was only a few years after Guth's paper. I mean, so this was in the 1980s. So it was pretty quickly realized that there was another way to do it, and this was called new inflation. And the difference is you didn't form bubbles, but the phase transition happened smoothly everywhere, and the particle production happened just as this thing settled down into its vacuum. So that basically the thing that's driving the expansion of the universe is the energy stored in this metastable or unstable state of this Higgs field. It has enormous energy. And it acts like an energy of empty space. This field is everywhere. It carries with it energy. And that energy of empty space acts like a cosmological constant, basically, except it can have time dependence. It can have dynamics. This was actually realized before Guth came up with inflation. So Linde wrote a paper in 1975, 5 years before inflation happened, pointing out that scalar fields like the Higgs could create an effective vacuum energy. And there was another guy who's less well known, who was actually my classical mechanics teacher in grad school, a guy named Joe Dreitlein, had written a paper at the same time. So Linde was still in Russia at the time, and so there wasn't a lot of communication. But so this was realized earlier than that. And then Guth realized that this would drive accelerated expansion and so on. But anyway, all of this energy stored in this field that is driving the inflationary expansion then gives you the energy. When that decays, it decays into particles in the standard model and creates a hot thermal equilibrium primordial soup. All the energy to heat up the universe afterward comes from the energy that was stored in this field.
Like a potential energy.
Yeah, exactly.
Yeah. So therefore, in this picture, the vast landscape of the volume, I don't even want to use the word universe because it's not really clear what it is, because it lives outside of our bubble universe almost. But the vast majority of it is still inflating.
This is the idea of eternal inflation.
Okay.
Now, so this was also not realized at the time. It was Linde quite quickly realized that this would create problems in terms of eternal inflation. So the idea is that you have this field that is stuck in some sort of unstable equilibrium, that it carries a lot of energy, and that energy causes this expansion, empties the universe of everything but that field. The trouble is that it's hard to stop. You can stop it locally, so this thing will maybe roll off, go through a phase transition at some local spot. And now, instead of like Guth's idea was that you had that phase transition happen in a bunch of places and then the bubbles all run into each other and everything smooths out. In the modern conception, our entire universe is just in one of those bubbles. Now, in between those bubbles, you're still inflating. So inflation ends locally, but there's going to be some other region way, way outside your horizon that's still going to be inflating. And then somewhere else, that's going to end and create another bubble that's going to have another universe in it and another bubble and so on. And so this is called eternal self-reproduction. So inevitably, in almost any inflationary theory you write down, what you find is that inflation will end locally and create a universe that looks like ours. But on larger scales, way outside our horizon, the universe is still, inflation is still going on and popping out more and more and more bubble universes, and this goes on infinitely into the future. Hence the title of the book.
Yeah.
And this is basically, inflation doesn't create just one universe like ours. It keeps going and keeps creating them indefinitely into the future.
So you use this analogy of a glass of beer in the book.
Yeah,
a few
right.
times.
So this is a glass of beer is an example of a first order phase transition. So you have carbon dioxide dissolved in the beer and it makes little bubbles when it comes out of solution. In this analogy, each of these bubbles would contain an infinite universe like our own. There's a cool trick in relativity that if I nucleate one of these bubbles, the bubble expands outward at the speed of light. But because the universe is inflation is happening, the universe is expanding so rapidly, these bubbles are being pulled apart from each other faster than the speed of light. But if I take a bubble that's expanding outward at the speed of light, I can change the way I think of time and space, and I can fold an infinite universe up into that finite bubble.
I want to come back to that, because that was the most mind-bending part of the whole book, and we need to spend some time on that. But
so yeah, to get back to finish up with the beer analogy, though. So basically, in eternal inflation, the beer is the inflationary space. The bubbles are infinite universes like our own, infinite flat universes, and they're creating just more and more and more of these bubbles as time goes along, like the CO bubbles coming out in a glass of beer.
So I want to ask you about the analogy to dark energy, because we do live in a universe which is expanding, as we talked about, and dark energy is this force which is causing, we don't really know what it is, but it's causing the universe to expand, and it's space, it's a force intrinsic to space itself, an energy intrinsic to space itself. So that seems like it has similarities to...
Deep similarities.
Yeah, and I guess the question is this a completely different beast that just happens coincidentally to have similar properties, or are these somehow interrelated to each other?
I wish I knew the answer to that question. I mean, nobody really knows. Both of them are very mysterious.
They're both scalar fields, right? So they're both...
Yeah, so it depends on what the nature of the dark energy is, which we don't know. It could be driven by something like a scalar field that drives inflation, or it might just be something where empty space has an intrinsic energy density. It's just entirely unknown. But they are similar in one really important respect, which is that, mathematically, the way you define inflation or not inflation is whether or not the expansion of the universe is speeding up, right? So if I have a universe that's dominated by dark matter or by photons, called matter-dominated or radiation-dominated, what you find is that, as you would expect, right, the universe is expanding, but it's full of stuff, so the mutual gravitational attraction of everything tends to slow that expansion down, right? And in this case, you see more and more and more of the universe inside your observable horizon as time goes along. The opposite case is in inflation, or as in the case of dark energy, right? When they discovered dark energy, what they did was they went out and measured the expansion rate of the universe at very high redshift, which meant at very large distances, which meant they were measuring how fast the universe used to be expanding. And they found that they expected to see the universe slowing down. And instead, they found that it's speeding up, which was a big surprise.
We had Adam Rees on the podcast, so
yeah. That's great. Yeah, go watch Adam Rees's episode, and but this was a huge surprise, and that is basically what inflation is accelerated expansion.
Right.
Except in the early universe inflation, it's incredibly fast. The acceleration happens at an enormous rate compared to the dark energy today, which is much more modest.
Yeah, it almost seems like if you had there's these ideas like phantom dark energy, where the dark energy grows in time, and you get these kind of big rip type scenarios
where
in the future.
the expansion speeds up so fast that it actually tears the universe to pieces.
Yeah, and those sound that end point sounds similar-ish to this inflationary universe. It almost feels like the universe then ended up in this zero dark energy initial state. The inflaton collapsed. We ended up with just the energy of that initial reheating, as you describe it in the book, that causes expansion. The gravitational matter wants to collapse the universe back, but the energy keeps expanding it. But the dark energy then starts to grow, let's say, over time, and cause this expansion to get more and more rapid. And eventually the end point, the asymptote of this, is that you end up back where you started, that the universe empties out because that's why it feels like
Katie Fries and I actually published a couple of papers on a model where it actually bounces back and forth between a sort of a big rip and inflation. Where you add modifications to the equations for gravity such that instead of a big rip, what you have is the universe bounces back. And so you're essentially bouncing between a big rip and an inflationary expansion.
But I guess I don't quite understand why these are discrete, because to me they almost seem to be the same thing. At least phenomenologically, they seem to be doing the same thing.
Yeah, well, let's take the case of a cosmological constant. The big rip has its own problems, but so if the idea of a cosmological constant, which is certainly consistent with what we see in dark energy, is the idea that just empty space has a little bit of energy, and that, it turns out, causes the expansion of the universe to speed up. And the end state of that is like the end state of inflation, where everything gets emptied out, and eventually you end up with a universe that's totally empty. This is because essentially, if the expansion is accelerating, instead of seeing your horizon containing more and more and more of the universe as time goes along, your horizon contains less and less and less and less of it. This is how inflation solves the horizon problem, is that you start out with two observers who are causally connected. If the expansion is accelerating, they will eventually be moving away from each other faster than the speed of light and become causally disconnected at late times. And this is precisely how inflation solves that causality problem, makes the CMB smooth on scales larger than the horizon and so on. Dark energy does the same thing, right? So if the dark energy continues to dominate, galaxies that we see today that are moving away from us less than the speed of light will be moving away from us a little bit faster, and eventually a little bit faster, and eventually they'll be moving away from us faster than the speed of light, and they'll disappear from our observable universe. So the end game of a cosmological constant dominated universe is our local group, us and Andromeda and a few other galaxies that we're gravitationally bound to, will be alone in a completely empty universe. And in fact, you work out the numbers, and this will happen long before all the stars burn out, so that our distant ancestors' cosmology will be impossible for them. So this is another weird fine-tuning, is that we happen to live at a very brief time in our universe where it's possible to even do cosmology. Our distant ancestors 100 billion or 1 trillion years from now won't have any galaxies to look at and won't be able to measure the expansion of the universe.
No matter how good their telescopes are.
That's right, because there's nothing there to look at.
So, okay, so let's change gears a little bit. I wanted to ask you about this inflationary field. So we're kind of invoking this thing called the inflaton. This
we don't know what it is.
And I guess that's where maybe some people might feel a bit of discomfort, because it just feels like we're inventing something. Is there any connection to the standard model? Could any of our known particles potentially serve this role, or would it have to be another particle that we add to our roster?
The simple answer is probably some other unknown phenomenon. And we just give it a name. Really, it's an order parameter for a phase transition. And that could take on it could be a composite thing. It could be a collective effect of some other physics. It could be a fundamental field like the Higgs boson. It could be many things. And in particular, for example, in when people make models of inflation in string theory, the thing that takes that order parameter, the thing that is the field that drives inflation, is actually related to how you fold up multiple dimensions into smaller levels of dimensions. And that creates these essentially parameters that are how you folded that space up. And those things can drive inflationary expansion. So in string theory, inflation is driven by the way space is compactified. These are called moduli fields in string theory. So there are many, 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 many things that this field could be. There are models that people have proposed in which it's the standard model Higgs that does this. That you have to work hard at it.
So the Higgs could be the
Yeah, the problem is that just the standard model Higgs and standard gravity, it doesn't work. The potential is too steep. You have to have something where inflation has to last long enough to solve all these problems, to drive the universe to flatness, to solve the horizon problem. So you can put a lower bound on how much expansion has to happen during inflation. It's about a factor of 10 to the 26th power. It's a lot, right?
I think you mentioned there's like you need at least 80 doublings in the size of the universe.
Yeah, right. So that's about 10 to the 26.
Okay.
Or usually, more technically, theorists will refer to the number of e-foldings. So it's e to a certain power, and that's about 60. Mm-hmm. Inflation can go on for much longer than that, but it has to go on for at least that. And in order for that to happen, this field has to be rolling very, very slowly along this potential surface, which means that it has to be flat. And the potential for the Higgs boson isn't flat enough. It won't last long enough. The way these models do it is then they modify gravity. They couple it to gravity in certain ways, and they do all these technical tricks in order to make it work. But just the regular standard model Higgs and regular gravity, it won't work for inflation. You have to mess with it.
So this is a decay from, compared to the analogy of phase transition. We're transitioning from some higher energy potential energy state to a low energy state, which we call true vacuum. And I guess the question is there another state below that? How do we, sometimes people talk about this, the false vacuum idea. That
and there's one of the weird properties of the Higgs that we've figured out is that it appears to be right on the edge of instability. So depending on the other parameters of the standard model, our vacuum may or may not be stable, right? And you can measure these parameters. And it turns out that we're right on the boundary between whether or not the vacuum of our Higgs field is stable or unstable equilibrium. And
within like a couple of sigma or something?
Yeah. I mean, it's a really, there's no reason for it to be that close. And we have a certain degree of evidence that we have a stable vacuum since we're here.
Yeah.
But that's a really neat doomsday scenario, is that if our vacuum were actually unstable and just had a very long lifetime, it could transition to a different state. All of the particles that make us up would all have different masses and couplings than they do now, right? And that would not be a healthy situation. And more to the point, that if that phase transition happened, it would make one of these bubbles that would expand outward at the speed of light. So you would never see it coming, because it would be coming at you at the speed of light. And so if that phase transition has happened out somewhere in the universe, it could be headed to us right now, and we would never know it. But all of a sudden, all the atoms in our body would just like suddenly become massless or something like that, which would, and just poof, you'd be gone.
Doesn't sound the worst way to go, to be honest.
No, we'd never see it coming, and it'd be quite peaceful, I guess. But it would destroy the entire universe.
But you'd put it, I guess, in the grander scheme of things, this is probably a fairly low probability thing to lose sleep about.
Yeah, if it was going to happen, it probably would have already, is the idea. Yeah. But so, in fact, we don't really even know for sure that the Higgs field is stable. We just sort of take it as a matter of faith. And weirdly enough, when we measure it, it happens to be right on that stability boundary.
Will future upgrades to the LHC or particle accelerators?
Yeah, I think they're going to be able to measure it better. Yeah, okay. This is an experimental question, remarkably enough.
That's exciting.
Yeah.
Maybe tell us a little bit more about this pre-Big Bang universe, or whatever you want to call it. Maybe it's not really the universe, but what does the inflationary pre-universe look like? Is it complete?
So this is another one of those overloaded words, is the Big Bang, right? Yeah. So sometimes when people talk about it, they mean the fact that the early universe was really hot and dense. And this was Fred Hoyle's original usage of the word. He used it as a pejorative to make fun of and it just stuck. I imagine, I don't know if anyone ever asked him what he thought of the fact that he actually coined a popular term when he was
turning his grave about that.
But also people refer to the Big Bang as being this initial singularity, right? This point of infinite density where the curvature goes to infinity and we lose track of the physics, right? In the cosmology of the 1970s, those two things were identical to each other. They happened at the same time. In inflation, you get rid of the singularity. You keep the hot, dense initial state, but that's now the end of inflation when this field decays into standard model particles. The inflationary phase happens before the onset of the hot Big Bang, the hot, dense initial state.
So there is a before. People say,
Right.
sometimes people say you can't ask what's before the Big Bang. It makes no sense. But in inflationary theory, you can ask.
You can't ask what's before the initial singularity. But what inflation does is it takes that singularity and pushes it off further into the past. Now, there's an interesting question. Can inflation push that initial singularity infinitely into the past? Can you get rid of it altogether?
Why is there a need for a singularity at all in inflation? Can't you just have an eternal state?
Well, that's a great question, right? And that would be the hope, especially since inflation is exponential, essentially. And if I take an exponential function, it only goes to zero at minus infinity, right? So can I have an infinitely old universe? Can I get rid of the necessity for a singularity? The answer is no. And this is the result of a very powerful mathematical theorem that was proved by Arvin Board, Alan Guth, and Alexander Vilenkin in the early 2000s. It's called the Borda-Guth-Vilenkin theorem, or BGV. And they showed that any inflationary space must necessarily still have an initial singularity or some initial boundary. You can't show that it's singular, but you can show that inflation cannot be infinite into the past.
So there's still a t equals 0.
Yeah, so there is still some initial boundary to inflation that remains unexplained, and you can demonstrate this in a very general way mathematically.
Is there a conceptual way to explain this beyond?
Well, so the way it works is this like neat trick of relativity, right? So if I take an observer who's just sitting still in the universe, called co-moving, right? And this is sort of a preferred reference frame. In an expanding universe, if I'm moving relative to this co-moving frame, I'll lose energy, slow down, and come to a stop, right? So in inflation, a co-moving observer will see the universe be infinitely old. But now suppose I have an observer who has a small velocity relative to that co-moving frame. As time goes forward, he's going to slow down and stop. So if I integrate that backward, if I look backward in time, means they must have been going faster and faster and faster. And so any observer at a certain point in this cosmology that has a finite velocity would have been essentially moving at the speed of light very early on, which means time dilation. They see time moving more slowly, and it turns out that along that path, what looks like an infinite amount of time to a co-moving observer is finite to the non-co-moving observer. And this is an idea in relativity called geodesic completeness. A space is said to be geodesically complete if every geodesic or freely falling observer sees their path through space-time be infinite in both directions. But if any observer sees their path end after a finite amount of time, the space is called geodesically incomplete. So for example, observers falling into a black hole hit the singularity at a finite amount of time. They're geodesically incomplete to the future. The Borda-Guth-Vilenkin theorem is essentially a proof that says that inflation is geodesically incomplete to the past, as a mathematically rigorous way of stating it. Because of the fact that you have these observers that actually, what looks like an infinite amount of time to an observer at rest looks like a finite amount of time to a moving observer because of time dilation.
So is this a failing then of inflation or a...
Yeah, well, it's just a property of it. It would be nice if you could just say, well, we've gotten rid of the initial singularity. The universe started out inflating and inflates infinitely into the future. It inflates infinitely. Internal inflation tells us that inflation is infinite to the future. The hope would be that it could be infinite to the past as well, and that just ain't so.
So at this t equals 0, there was absolutely nothing prior to it. It doesn't really make any sense to talk about prior to it. And then from nothing, we suddenly emerge with this inflaton field.
Yeah, so inflation emerged out of something else. And we don't know what that something else was. We just know you can show mathematically that if you inflated, that it had to come from somewhere. And the problem with this is that inflation acts like a giant eraser. Right? Whatever was there before got stretched out so much by this inflationary expansion. Remember, you have to have at least 60 E-folds or 80 doublings of the universe, but it could be a trillion, it could be a quintillion. Inflation could go on for quadrillions, whatever superlative number you want of years. Right? So this whatever this boundary is can be arbitrarily far in the past, and all traces of it, whatever the physics was at that boundary, have probably been completely erased by the inflationary expansion, and we have no observational access to it at all. So it's an incredibly difficult problem. You can prove that boundary must be there, but you can't observationally learn anything about what its properties might have been.
Yeah, that is a frustration, I guess, because it'd be nice if it tied up. It seems to tie up so many
Yeah.
things. And
But there's this giant loose end there, which is we don't know what initiated inflation.
is that the biggest Achilles heel, or are there other things that?
Well, the existence of a multiverse depends on your point of view. I mean, I think a lot of people would view that as being
These other bubble
this is all these
universes.
other bubble
Yeah.
universes. Like
Yeah.
that, this initial state, these things are so far outside of our horizon that there's no hope of us ever accessing them experimentally. Right? You can, in principle, have collisions between two of these bubbles. They would be very rare. People have looked for them in, for example, the cosmic microwave background and found no evidence of it. So if those other bubble universes are out there, they haven't run into ours. They're outside of our observable space. And so this becomes almost a philosophical question as to whether or not they really exist, right? Or what their properties are. This brings up this sort of anthropic logic as well, because, for example, if I make models of inflation and string theory, inflation is driven by these fields that determine how the dimensions fold up on themselves. And it turns out there are a lot of different ways to fold these dimensions up on themselves. People have estimated that the number of different stable vacuums in string theory, the number of different ways you can fold up these extra dimensions is about 10 to the 500th power, right? Which is just this ridiculous number. There are only about 10 to the 80th atoms in the universe.
Yeah.
So it's this mind-bogglingly huge number. And the idea is that there is no particular there's nothing that favors one way of folding these things up over another. So if you have inflation and string theory, you're creating all these bubble universes, and each of them would have completely different laws of physics in them because they would have different ways of compactifying these extra dimensions.
Yeah. Why is the compactification different in each bubble universe? Why couldn't they all just have the exact same laws of physics?
That's the other possibility.
Yeah.
There's no principle, at least as far as in string theory, that would guide this. That as far as I know, nobody has come up with a way to say, well, this is one of the big problems with string theory is there was originally a hope that there would only be one unique way to do this, that the laws of mathematics would tell us that there's only one way to fold up these extra dimensions, and it would give us the standard model in a universe that looks like ours, and that you could basically deduce all of particle physics from logical consistency. That was the hope a long time ago.
Yeah, I guess I'm just thinking that there's almost multiple axes of multiverse, right? So we have this one axis in inflation, which is...
That just tells you that there are regions of the space-time out there that are inaccessible to you.
Yes, and there are different bubbles within that where we have true vacuum. That is one axis of multiverse. Tegmark often talks about these many different ways of defining multiverses. You've probably seen like Everettian versions and stuff.
Yeah.
But
this is very different than like the multi-worlds interpretation of quantum mechanics, which is an entirely different beast.
Completely
right?
different.
Yeah.
It's actually, I think it's similar to what Tegmark calls the type 1 or type 0 multiverse. That if you just travel far enough in one direction, you know everything repeats, and you can end up in totally causally disconnected regions, which are...
Well, even in a non-inflationary Big Bang universe, a flat Robertson-Walker space is infinite in extent. So we have our tiny little observable bubble here, but there's an infinite amount of universe out there, right? That is, in a sense, that's an almost trivial multiverse, right? Yeah. Inflation dresses that up a bit, and that we have this inflationary space that is creating multiple versions of these infinite universes. So now we don't have just one infinite universe, we have an infinite number of infinite universes. And then things like string theory tell you, well, then we shouldn't expect the laws of physics to be the same in those universes. And so that's adding yet another level of dressing. So you don't need to have that. Inflation tells you that you're going to have all these bubble universes, but it could very well be that it's a Copernican multiverse, in that everything is pretty much the same everywhere.
What do you call the stuff in between the bubbles? Is that like...
That's inflation. So this is...
But what is that region? Is it the bulk? Like, is there a name for that?
I don't know that there's a single technical word for it. Yeah, the bulk, or the inflation, the inflating bulk spacetime. Yeah. Okay. I don't think it really has its own terminology that I'm aware of that is in any way standard.
I guess I just wanted to be clear, because there are so many different versions of multiverse and so many different versions of like brains, clashing into each other. And this is completely different to those.
Yeah,
ideas.
Well, and that depends on the model for inflation that you use, right? So you can create inflationary models where you have these higher dimensional brains that are smacking into each other, and that's how you reheat things up and create standard model particles, and
which
so
is
on.
Closer to Guth's idea.
Yeah, in some ways, yeah. Although it's in detail, it's very different than the way he envisioned it.
Okay.
But so one of the themes in this book is arguing for a more Copernican viewpoint, this idea that the expectation here would be that these other universes would be more or less the same as the one we live in. This is a basic, so this is extending the Copernican principle beyond, so Copernicus said, well, the Earth is not unique, or the solar system is not unique. There are other solar systems and so on. And this was one of the real heroes in the book that I talk about is the Renaissance philosopher Giordano Bruno, who was really more Copernican than Copernicus. He really took it to its logical conclusion, saying that there would be other Earths, and there would be other civilizations there, and that an infinity of worlds is actually a quote from Giordano Bruno.
Exoplanet people use that quote. You've seen many an exoplanet talk start with that quote.
Yes.
It's a little bit cliche almost, an exoplanet field, yeah.
Well, but in this case, it would be an infinity of universes.
Yeah.
So it's taking Bruno's idea even further. But I guess the argument that I try to make in the book is that this is exactly what you would expect from a Copernican viewpoint on the universe, is that, our solar system is not unique, our galaxy is not unique, why should our universe be unique? And that, in fact, there are probably other, inflation tells you that there are probably other universes a lot like ours out there that we just can't get to, and that this is actually very consistent with a Copernican viewpoint on the universe.
Doesn't inflation violate the cosmological principle? Because this bulk, whatever you want to call it, is no longer homogeneous.
In some average sense, it would be, right? So you're just producing bubbles at a constant rate, and so that if you sort of looked at the bulk in really large scale, it would be like that glass of beer that would just have a bunch of bubbles in it, so it would be a little inhomogeneous. If you zoom out far enough. Yeah, if you zoom out far enough, it would become homogeneous.
True, but then we also live in a fairly special region because the vast...
Well, like we live in a special region of space because we're in the solar system, right? But there are lots and lots of solar systems. So it would be, that ends up being a manifestation, another way of thinking of the cosmological principle, if you like.
Mm-hmm. Okay. So you describe in your book how a generic prediction of all inflationary theories is the production of gravitational waves, which in this case would be primordial gravitational waves, not the type that we've seen with these merging black holes that LIGO has detected.
That's right.
These are sort of nascent to the universe itself. So maybe let's walk through why is that prediction always occurring, and is there any chance of detecting them? Yeah, well,
this phenomenon ends up being a super important part of the story, right? So we talked about how if you have accelerating expansion, it flattens the universe out. So if you have some curvature there, right, if the universe is positively or negatively curved, inflation drives it to flatness. Yeah. And because of the fact that things are expanding so rapidly, they get stretched out well beyond the scale of the horizon. So it solves the horizon problem as well. Those in and of themselves would not really be sufficient to say, oh, I really believe inflation is a fully scientific theory, right? Because maybe you could imagine that the flatness and the homogeneity could happen as a result of some kind of a boundary condition, for example, right? I love the famous quote from Alan Turing, who wrote that physics is a differential equation, religion is a boundary condition, right?
Yeah, that's a good quote.
And so you could imagine that it could be set by some symmetry or something like that, right? So you want to have a higher standard for what you say. Why do I believe that inflation is a good theory, right? Why is this such a strong candidate as a theory for the early universe? And the reason for that is inflation gives you something else for free. So when I write down a theory that has this accelerated expansion that solves all of these sort of like large scale problems in the universe, well, this thing that's like a Higgs boson or some modulus field in string theory or something like that, it's going to be a quantum object, and the real magic happens when you include quantum mechanics, because of the fact that this field now not only is this classical thing that's driving this expansion, it actually has quantum fluctuations. The quantum mechanics makes it bounce around a little bit. And those quantum fluctuations get stretched out. The inflationary expansion takes these little vacuum fluctuations at small scale in the universe, these little quantum fluctuations that happen everywhere in space, right? Part of quantum field theory is that if you look at the vacuum at very, very tiny distances, you're going to see these little virtual particles popping into existence and disappearing again, right? This is just a consequence of the Heisenberg uncertainty principle. And now if I add inflation, those virtual particles get stretched apart so rapidly that they never have a chance to recombine. This is very similar. There's a cartoon picture of Hawking radiation, the fact that black holes radiate. This is a very famous result from Stephen Hawking. A cartoon way to think of that is you have these virtual particles that are produced near the black hole horizon, and one of them disappears into the black hole and the other one is radiated outward, right? The real math of it is more complicated than that, but it's sort of a basic way to understand it. In inflation, it's a similar process in that these virtual particles, essentially before they have a chance to recombine, they're moving away from each other faster than light because the expansion is so rapid. And so there is a phenomenon that is essentially exactly the same thing as Hawking radiation that happens at the horizon, the edge of the horizon of the inflationary universe, is that it radiates for the same reason that a black hole radiates, and it's related to vacuum instability, vacuum
So it's
fluctuations.
Hawking radiation.
Yeah, it's basically Hawking radiation. And this is inevitable. If I write down any inflation model, you're going to have this Hawking radiation that happens. And there are, it will radiate in two ways. One of them is it will create gravitational waves. And the strength of these gravitational waves is related to how fast the universe is expanding. The faster the expansion rate, the stronger the gravitational waves it produces. We don't know exactly how fast the inflationary expansion was. There are many orders of magnitude of freedom there. But if inflation happened at a very high energy and had an extremely rapid expansion rate, those gravitational waves would potentially be observable today. Either by direct detection experiments, like LIGO. LIGO is not sensitive enough to detect these, but you could imagine a future orbital observatory that would be capable of doing it. And there have been proposals to do that.
So there's also, even without inflation, we still have a horizon, a particle horizon in our universe.
Yes.
And does that not also Hawking radiate?
No, because the expansion isn't accelerating. Well, in fact, with accelerated expansion from dark energy, we would be producing very, very weak gravitational waves, but the expansion is so slow that they would be like practically undetectable.
Okay.
You have to have really high energies because gravity is such a weak force. And the other, so that creates gravitational waves, and the other thing it does is creates what are called curvature perturbations, or basically little fluctuations in the density of the background space-time. Essentially, this field is rolling down a hill. When it's lower on the hill, there's lower energy, and when it's higher on the hill, it's higher energy. So you can translate that into a density. So if it's bouncing around a little bit, there's going to be that bouncing up and down the potential is going to create little fluctuations in the density.
Just from uncertainty principle.
Right, exactly. And those get stretched out too. And in inflation, those are the source of the fluctuations that we observe in the cosmic microwave background. So we can actually see those. And in inflationary models, those initial fluctuations, so the cosmic microwave background is uniform to about a few parts in 100,000. But at the 1 part in 100,000 level, it's actually not uniform. If you look at the CMB sky, you see little fluctuations in the temperature. This was first discovered by the COBE satellite in the early 1990s, and later on by WMAP and Planck, and actually South Pole Telescope just released some new measurements of these fluctuations today. These little fluctuations in the temperature of the CMB are associated with fluctuations in the density of the plasma. And these are the things that later collapse under gravity to form all the galaxies and clusters of galaxies and so on, right? So this whole picture of the universe that we see today arose out of these tiny little density fluctuations. In inflationary theory, those were produced during inflation.
So these are the super horizon perturbations.
Right. And so these perturbations are stretched out to wavelengths that are actually bigger than the size of the observable universe. And we see those in the CMB. We can actually see that there are density perturbations that are bigger than the horizon size.
So what does that look like then? If I imagine like a sine wave that was the same wavelength as the universe, I could see it go down and then back up again. If I stretch that wavelength out longer, I would just see like a slope or something, like a gradient.
Well, when we look at the CMB, we see many, many, many horizons. So we can see these perturbations that extend larger than one horizon on the CMB because the horizon size at that time was so small. Right. And presumably inflation would have created fluctuations larger than our current horizon as well, but we can't see those because they would just look like a change in the expansion rate, basically.
Yeah.
Right. So the beautiful thing about inflationary theory is that when you postulate this crazy accelerated expansion to make the universe big and flat and old and all of these things, automatically you get for free, quantum mechanics gives you a source of the initial conditions for structure formation and predicts the existence of a background of gravitational waves. And both of these are very definite predictions that you can go out and check.
Do you not get if you don't have inflation, but you still have obviously quantum mechanics, does that still not give you just the, just have the Big Bang create a rapid phase of expansion, and within that initial seed of the singularity, or very slightly after the singularity, you have quantum fluctuations? Could those not also form the seeds? Like, is the seed problem?
No, because they wouldn't be stretched to superhorizon wavelengths, right?
Okay.
So the fact that we see these density waves that are bigger than the size of the observable universe can only come from inflation.
But you'd still get structure.
You could. Right?
Yeah.
There are various other ways to form structure. Sort of the main competing mechanism for structure formation that was around in the 1990s was topological defects, right? So this is essentially if you have like the Higgs field, right, is relaxing from. So when the Higgs phase transition happens, the Higgs field starts out and all the standard model particles are massless, and then it rolls down and the standard model particles acquire mass, and this, through this phase transition that happens at about the same energy as the LHC probes, right? That's why the LHC is at that energy as it probes that phase transition. This would have happened in the early universe, and if this happened in a bunch of different horizons, right? If these regions were causally separated from each other, the Higgs would roll down to different places in different parts of in different horizons of the universe. And then when they finally all met up again, when the horizon got bigger, they would have different vacuum states. And these would create things called topological defects, right? So an example of a topological defect is this kind of phase transition is domains in a magnet, right? Where if you magnetize some metal, you'll have one little microscopic domain that's going to be magnified in one direction and another microscopic domain that's magnified in another direction. And the boundary between those two things would sort of interpolate. That's an example of a topological defect in condensed matter. Yeah. The same thing would happen cosmologically, and this would actually create density perturbations that could sort structure. That is, we have seen no evidence for this happening. It's called the Kibble mechanism. And one of the big mysteries is why it didn't happen. You would expect it to be inevitable, and we don't see any evidence for these cosmic strings or other kinds of topological defects in the universe. So that was a competing theory for structure formation before inflation basically won when we actually looked at it. So the difference is that they would have very different signatures in the cosmic microwave background. If topological defects were forming the structure, the CMB would just be this one big amorphous blob. The fluctuations wouldn't have any structure in them. What we actually see is that there are these acoustic oscillations, that everything is very neatly in phase. And that is a prediction of inflation that was not a prediction of the competing theory.
Okay, so we have two predictions, I think, then here, that on top of solving the problems of the horizon problem, the flatness problem, we also have the prediction of super horizon perturbations, which we've confirmed in the CMB.
Yeah, that's right.
And primordial black hole, primordial gravitational waves.
Which we have not yet confirmed.
Yeah.
Right. So those have not yet been observed. And this, in fact, was the other way you can look for them is in the polarization of the cosmic microwave background. And this is very famously like Brian Keating's book, Losing the Nobel Prize.
Yeah. He was on here talking about that. Yeah.
The claim that they were making was they had seen the sign of these primordial gravitational waves in the CMB from inflation, which was incredibly exciting. Yeah, I mean, that would mean that you're actually looking at gravitational waves that are propagated to you from before the onset of the hot Big Bang. It would have been just an absolutely transformative result. And that's why everyone was so excited about it and why it was so disappointing that it turned out not to be true. Yeah. We are still looking for those signatures. So there are new cosmic microwave background measurements. Brian is one of the people involved in those who are going out and looking for these more subtle signals of sort of a lower amplitude of gravitational waves, but they have yet to be found.
But it sounds like inflation is flexible enough that even if we never detect these in a next 100 years of upgraded detectors, that still doesn't rule out inflation.
They might still be there, but just too weak to detect. There's an unfortunate property here, a scaling law that happens, which is we don't know the energy at which inflation happened. It could be very, very high, or it could be much lower. There are many, many orders of magnitude of freedom there. The gravitational wave amplitude, how strong these gravitational waves are, depend on the fourth power of that energy. So if I change the scale of inflation by a factor of 10, that changes the amplitude of the gravitational waves by a factor of 10,000.
It's like the Stefan Boltzmann law.
Yeah, exactly.
T to the fourth.
Very steep.
Yeah.
So that means that we will only be able to detect those, even with the most advanced experiments that we can imagine, if inflation happened near the upper limit of the energy range available to it.
Does that mean that the number of foldings would have been close to the minimum?
No.
The doubling, sorry?
No. So that you would still require, the number of doublings you require depends weekly, logarithmically on the scale. So if inflation happens, for example, at the grand unified scale, about 10 to the 15 billion electron volts, you need 60 e-foldings or 80 doublings. If it happens lower, for example, if it's all the way down to the standard model Higgs, you only need about 20 or so.
Okay.
Right.
Okay.
So the number of doublings you need is weakly dependent on the energy scale, but the amplitude of the gravitational waves is strongly dependent on it. So that if inflation happened at the scale of the LHC, for example, the gravitational waves would be too weak for any conceivable experiment to measure them.
So when the super horizon prediction was confirmed, was that COBE or was that WMAP?
That was WMAP, right? So that there are, you see fluctuations in COBE that are bigger than the horizon size, but there are foreground effects that can cause that, in particular a thing called the integrated Sachs-Wolf effect. So in order to get a clean signal, one where there's no intervening galactic physics that could create something that would smear it out in that way, you have to look at the polarization, and in particular how the polarization and the temperature fluctuations themselves correlate with each other. It's called the TE correlation function. And that, there's a very clean signal, which is that there's a bump that is bigger than the horizon size on the CMB that can't be created by anything else. It's a real smoking gun for this.
So it kind of sounds like even with that, because the theory was developed in the 80s, WMAP was flying 90s?
2003 was when the first WMAP data was released.
So it definitely is a true prediction.
Yeah, I mean, and I remember seeing at the time, that's when I will shave my head and join the cult, is if we see these super horizon perturbations, because inflation is pretty much the only way to do it.
Yeah. So I guess what is the current status of inflation, and does it mean that with that evidence in hand, we're done? We can feel confident it is the correct answer, or it is
certainly, in my opinion, by far the best answer we've come up with. You can look in general, say, what are the most general properties under which you would create super horizon perturbations, assuming that like general relativity holds, for example. I wrote a paper a number of years ago with Ghazal Geshnasjani at Perimeter Institute and my graduate student at the time, Azada Mordinejad, where we looked at this question. And you can show in basically so that what you see in the CMB is you have super horizon perturbations at least about a factor of 1,000 in wavelength, right? If you look at that, the only ways you can do that are either by accelerated expansion. You have to have a speed of sound at least 10 times the speed of light. You could do it that way. So this is like these variable speed of light theories. Or if none of those other things, then you're driven to energy densities that are larger than the Planck scale inevitably, as long as you assume general relativity and an expanding universe. So inflation is basically, unless you want to have these weird superluminal theories, inflation is like the only way to do it, as long as you're doing it in an expanding universe. The loophole there is you could have a contracting universe. So these bouncing theories, for example, that are favored by Paul Steinhardt, create these super horizon modes because the universe is contracting and the horizon is getting smaller. And you have similar effects that could create a similar spectrum of perturbations. One difference between these contracting models and inflation is that they don't predict the generation of gravitational waves. So a detection of a gravitational wave background would be a really unique signature of inflation.
You think that would convert everyone if we got that?
Not everyone will ever be converted. Scientists are too contrary.
Yeah. How canonical is the theory? Is that if you were to take a poll of cosmologists, is it sort of widely accepted that inflation is the answer, or is that how many holdouts are there?
In the language of modern political parlance, I'd call this an 80-20 issue.
Okay. The Pareto rule. Yeah.
So inflation is on the 80 side. I would say that if you looked at, it really is an essential part of the standard cosmological model at this point. And there is a population of, heretics who are saying, no, I want to come up with an alternative to this. And this has actually been a very productive exercise because it's really, very much explored the phase space of cosmological theories that could produce this. But inflation is a very simple, straightforward way to do it that only relies on physics that we know is out there. We know there are scalar fields that have potentials that are capable of driving inflation. We have the example of the Higgs boson. It's basically something that is just like the Higgs, except a little bit different in detail would do the trick just fine. This is the remarkable thing, is that the simplest possible inflation theories do the job really well. They explain all the data we see. And that did not have to turn out to be true. So for example, the simplest inflation models, ones that only involve a single field like the Higgs, predict that these quantum fluctuations will have Gaussian random statistics. They'll be distributed on a perfect bell curve. If there are other things, if you have multiple fields involved, or some of these colliding branes, or some of these more elaborate theories predicted that these statistics would deviate from Gaussian random in calculable ways. And this was a very big trend in like the early 2000s, people calculating these non-Gaussian signatures. And Planck satellite, the European CMB satellite, was highly sensitive and was capable of detecting these non-Gaussianities, and they went out and looked for it and didn't find them. And so it sort of killed off a lot of these crazier ideas, because there were a lot of theories that predicted these non-Gaussianities would be really big and Planck would be able to see them. And if that had been the case, then it would be great, because you could have learned all kinds of things about the details of the particle physics. But for some reason, the universe, just like the simplest possible solution, a single field like the Higgs, does the job perfectly. And
Occam's razor.
Yeah, exactly. So
I guess it's a healthy state for the field to be in, actually, to be 80-20, because we were talking a little bit before we came online about how some commentators have said, it can seem from the outside like there's a cabal, like we're all kind of in this conspiracy of trying to push specific ideas just to keep ourselves on the payroll. And I think it's actually really healthy to have 80-20, because then the 20 can publish ideas without necessarily a threat to their livelihood, right? It's possible to be a critic without burning your career down the drain, and that makes for a healthy scientific dialogue.
I completely agree. Yeah. And there certainly is no cabal of inflationists who are out there destroying the careers of people who like do ekpyrosis or something like that,
Yeah, thank goodness. Yeah. So all you guys can keep going.
It's a very healthy debate, and the fact that there is a debate is a healthy thing.
Good. That's good to know. Now, I wanted to come back to this point. You mentioned this a couple of times, and I had to read this quote so many times in the book, and I still can't get my head around it. So, each bubble universe like our own appears finite to an outside observer. So we're outside the bubble. It looks like a bubble. You can walk around it. You can look around it. You can see this finite
little
bubble.
Sphere. Yeah. Expanding outward at the speed of light.
Okay. But, to continue the quote, but appears infinite to an observer such as ourselves inside the bubble. That is completely mind-boggling. And then you also say we borrow from an infinite reservoir of time to turn the interior of a spatial finite bubble into a spatial infinite universe. So this requires some explanation, right? Because I guess if I was to sort of cheat, maybe this is a good thought experiment. If I was to cheat and I had some FTL system, some faster than light ship, doesn't matter on the mechanism, but I can somehow travel faster than the speed of light, and I just kept going in one direction, it sounds like in this picture, I would never be able to escape my bubble.
No, you wouldn't. Yeah, that's right.
And that, I guess that's weird, because it sounds like in this book, there are regions, and when you hear the phrase regions, you imagine that that's something you could traverse and enter and exit. But help me understand, it's like a Doctor Who TARDIS type situation here.
Yeah, or something out of Harry Potter, some box that has an infinite interior or something. Yeah. So, right, an observer in the bulk, somebody out swimming in the beer and out in the bubble, would see these bubbles of true vacuum nuclei. And these bubbles expand outward at the speed of light. But because they're moving away from each other faster than the speed of light, they never run into each other.
So far, so good.
Right.
Yeah.
But this bubble expands outward at the speed of light. And in relativity, space and time are malleable, right? If I change my coordinate system, I can view time as space, right? So that, for example, even in special relativity, a moving observer, space and time exchange identities to a certain extent, right? And so what you're doing here is you're defining what you mean by space inside the bubble in such a way that you have an infinite amount of time to borrow from. So I can borrow a little bit of that infinite amount of time and create an infinite amount of space, right?
That's the infinite future of the universe?
Exactly. Right.
Okay.
So you're borrowing time from the future and turning it into space in the present. And so the bubble wall that looks like the edge of the spherical bubble that to an observer in the bulk is moving outward at the speed of light, to an observer inside the bubble, it is actually everywhere in their past. That bubble wall is the Big Bang. It's a moment that exists only in the past.
So in this infinity universe on the inside of the bubble, there's infinite space.
Yeah.
From the outside, there's infinite time, and it's exchanging those two.
Exactly.
So, there's infinite space? Does that mean there's infinite energy, mass, content, essentially inside this? Like, if I kept going, do I just eventually run into emptiness, or do we just eventually run into me and you having this conversation against someone else?
Well, it's a universe that looks like ours, basically. So a flat or an open cosmology, you have an infinite amount of space in them, right? And so it's homogeneous and isotropic and spatially infinite in extent. You can fold one of those up into the interior of a bubble that is expanding infinitely forward into the future. So in fact, if you do this naively, so you create an empty bubble, that the universe that you create actually has negative curvature. And then if you can continue to inflate, a little bit of vestigial inflation happens inside the bubble and flattens it out. There were some theories early in this idea came about in the 1990s when people came up with these models of inflation called open inflation. Back before the discovery of dark energy, there was a debate between theorists and observers in astronomy, because the theorists said, well, inflation tells us the universe has to be flat. Omega is equal to 1. A flat universe is the only sensible solution. The universe really must be flat. The observers went out and said, well, I'm sorry, we can only find 30% of the density that we need to flatten the universe. So people who went out and measured the masses of galaxies and motions of things, they said, well, the matter density is only about 30% of what we need to, 25 to 30% of what we need to have a flat universe. The universe is probably open. And this was a debate between experimentalists and theorists. So the theorists said, oh, symmetry tells me I'm so smart that I can tell you the universe has to be flat. And the experimentalists went out and said, well, I went out and looked at the universe and it ain't, right? In this case, it turned out the theorists were right. And it was the discovery of dark energy that made up the extra 70% of that closed the gap. And I think sociologically, this was one of the reasons why dark energy was so quickly accepted, was because it resolved this dispute and gave you a flat universe very neatly. But at the time, people came up with theories of inflation where they had these bubbles nucleate, and then you only had a little bit of inflation inside the bubble, and so you could create an open universe this way. And so it was a way of creating a negatively curved universe, but still preserving inflation. And those have since fallen by the wayside, since we end up living in a flat universe, and they're not necessarily. They're very contrived models. They're really hard to build correctly, and it's kind of nice that we don't have to worry about them anymore. But this was when it was first realized that you could do this trick with these bubbles.
So anyone inside these bubbles are truly trapped.
Yeah, because you would have to travel back before the beginning of your own local universe in order to escape your bubble, because the bubble wall is in your past. It's not a boundary out there in space at all.
Yeah.
And it's just a beautiful thing, isn't it?
It feels like we're going to talk about a Chris Nolan film or something at some point.
Yeah. It's like, how do you do that?
Yeah. So, and the boundary, you just want to touch on this more quickly. You said the boundary expands at the speed of light from observers in this book. Does it have to expand at the speed of light? Like, why is it the speed of light?
Typically, it will be if it's nucleating a bubble of true vacuum in a false vacuum with a scalar field. You work it out; that boundary will expand at the speed of light. You can come up with field theories in which it would expand at less than the speed of light as well.
And if it was expanding less than the speed of light, does that break this infinity?
No, not really. It still work out okay. I mean, if it expands at a third of the speed of light, you're still all right.
So the volume of habitable real estate then is not just, even if there was just one bubble, we'd say it's infinity, but now it's almost infinity to the power of infinity squared.
That's right. Yeah. So each bubble contains an infinite space, and there are an infinite number of bubbles.
Is there a super infinity that mathematicians have for handling something like that, or is it still just infinity?
Yeah, I'm just a silly cosmologist. I don't know.
It me-
Presumably, this is the kind of thing that mathematicians deal with all the time.
yeah. Now, this is all a product of eternal inflation. So, this seems like a point where you might imagine critics thinking this has gone too far, right? This is getting a little bit crazy. We've got infinity universes, infinity space within each of them.
And in fact, these 20%, these critics of the inflationary theory very, often point to this as being this absurd result that comes out of this, that, you write down this theory that does these things, and then you end up with this ridiculous answer that comes out the other end. Mm-hmm. And they kind of have a point. Yeah.
So yeah, I guess that's whenever you have a theory which is going to explain, it's infinitely malleable in this sense, and we've got infinities involved. It always seems precarious. But are you okay to stomach that, or does it bother you that you have this infinity of infinities?
This to me comes back to being a Copernican argument. And it's completely consistent with a Copernican view of the universe. And so to my mind, the way I philosophically resolve that problem is that, it is something that's consistent with a sort of the cosmological principle, if you like, or the Copernican principle. It's a very, very old philosophical idea that has proven itself pretty durable over the last few hundred years. So in that sense, it doesn't bother me. And this is one of the reasons why I, talk a lot about the Copernican history and Bruno and all of these ideas in the Renaissance up to the modern times, because I think that this is really just a very natural extension of it, and isn't something that really should be all that bothersome necessarily.
Yeah. Although I guess if you were a Karl Popper fan, you would maybe start to get uncomfortable at these other universes because
there's certainly no way that you can ever prove that they exist. They have no observational consequences at all. Right. And so this puts you really at the boundary of what you mean by a scientific theory or not. On the other hand, inflation itself, just basic inflation, makes a number of really detailed, definite predictions that you can go out and test. And we've tested a bunch of them, and a lot of them have turned out to be true. There are some other ones that we haven't been able to test yet. For example, the presence of primordial gravitational waves. Also, even the simple single field inflation models predict a certain small deviation from Gaussian random statistics in the fluctuations that is in principle observable. It's a couple of orders of magnitude below our best measurements right now, but it's not something that, for example, if we had a radio telescope on the moon that was looking at 21 centimeter radiation, you could conceivably actually get down to this point. So there are a couple of predictions of inflation that are still out there that we could get at, but Gaussian random fluctuations, super horizon scales, there's this idea of adiabaticity where they're all in phase, so it creates these coherent acoustic oscillations that we see in the CMB. All of these are non-trivial predictions of inflation that we went out and tested, and they turned out to be right. And if you want to, if you want to pull out Popper, there you go, right?
Yeah, I guess this kind of comes down to your philosophy of, and generally everyone's philosophy about what is really true. The true nature of reality. And, I remember hearing when I was lectured about quantum mechanics as a student, my professor used to say to me, don't necessarily think this is a true description of reality. This is just a model which works. It's just a mathematical model which makes incredibly accurate predictions as far as we can tell, but there may be a deeper theory behind this that we're just yet to discover. And I always liked that idea of thinking of theories as just essentially tools, mathematical models, which at some point will maybe crack and find beneath it. So in this case, you have a theory which makes a bunch of predictions, or a bunch of, I guess we could use the word predictions, and some of them are observational predictions. And then there's this other branch, and this branch of this tree of all these predictions, and one of those branches is this uncomfortable one because it's fundamentally not testable, which is you have these other universes. So does that mean, in your mind, do you have to accept the whole tree? Do you, as like, this is really true, this whole thing is really true because the other four branches work out? Or is there a way in your mind that you can say, well, I'm just going to accept that these four work and we can almost leave this one off for debate?
Yeah, I mean, this is a problem that cosmology brings to the forefront in the way that few other scientific endeavors do, I think, is that what do you do as a scientist when you have a theory that makes a bunch of testable predictions that you can test, but then this theory also makes a bunch of other predictions that you can't ever test, even in principle, right? And how seriously do you take those things? And so, and when, especially when you have a theory of inflation that straddles those two things, right? That makes concrete observational predictions and also has these really weird philosophical repercussions that you don't know how to cope with. I don't have an answer to that, right? As a scientist, I want to understand where where galaxies came from and how the universe worked and all that kind of stuff. But cosmology is weird in the fact that you're studying the universe as a whole, and you inevitably bump up against these questions that are no longer properly framed scientific questions at all.
But do you have a personal belief on it? Do you subscribe? Do you think there really is this infinite of worlds out there?
I don't see any reason not to.
That's still dancing around the question.
Well, no, it's not a matter of faith. I don't know, right?
Yeah.
And there is that distinction. There are things you can know and things you can't know. And one of the inevitable problems of being a cosmologist is you end up running into both kinds of things, and you have to be able to hold them in your head at the same time, because your theories will have these properties. And ultimately, I think we just have to learn to live with that. These are limits of science, in much the same way that quantum mechanics introduces limitations on what we can know about a system, right? So there is a certain similarity here with the problems that are brought to the fore by quantum mechanics, because quantum mechanics essentially is a theory that tells us that there are these fundamental limitations to what it is that we can measure about the universe, and that there's no way to get around them. And physicists do not like this. And cosmology does this, except on larger scales, but I think they're related in that way, that there are basically, physics is telling us, the laws of physics that we can measure and validate and actually have some sort of scientific certainty about, tell us that there are other things that we can never know. We can't see things beyond our horizon. We can't measure the position and momentum of a particle to arbitrary precision. And in many ways, the story of 20th century science is realizing that these limits exist in ways that I think that 19th century physicists didn't.
So it's almost hybrid in the Popperian definition, that you have aspects of the theory which are clearly testable and thus scientific, falsifiable, and aspects of the theory which are not. So I guess the question is, where does that make the final compound theory scientific or not? And you could, by extension, you could say this the same thing about like string theory or other multiverse variations, not just inflationary. Is the multiverse scientific generally if it makes some of its aspects can be tested but others can't?
Yeah, I mean, with string theory, you could imagine that in principle, I could create a particle accelerator with high enough energies that they would excite stringy degrees of freedom, and I could test it, right? There's no physical principle that prevents that. It's mostly a technological limitation, right? You'd have to build such a ridiculously gigantic particle accelerator that it would be impractical.
Yeah. It may as well be not practical.
That's right, but there's a distinction between something that is untestable because it would be impractical to test it, and something that is untestable because it is fundamentally forbidden to be able to test it. It's built into the theory. And the inflationary multiverse is one of those latter categories, unlike, for example, string theory, which is just untestable in practice rather than untestable in principle. And I think it's important to make that distinction between these two problems. So people complain that string theory is untestable, but it's not fundamentally untestable at all. It's just that we're like sort of small pieces of meat who can't manipulate the universe well enough to do it. In the case of the multiverse, it doesn't matter. We could be gods, and we would still be unable to test the theory.
So is eternal inflation a scientific theory? Yes, no?
I would say no in that sense. It's a consequence of a testable scientific theory, but in and of itself, it has no particular scientific, because it has no observational consequences.
So there was another. I kind of want to rewind slightly. We talked about these bubbles and these other universes, which obviously are out of contact with us. You did have a quote at one point that caught my eye in the book. You said sometimes two of these bubbles can collide. And obviously, you've kind of mentioned that was almost the origins of the idea with Alan Guth. But at least in the modern picture, this seems, help me understand how that can happen. Because if these bubbles are in this beer and they're moving away from each other faster than the speed of light, how could they ever come into contact with another one?
If if the bubbles nucleated close enough to each other, remember they're expanding outward at the speed of light, so that if you get enough bubbles that nucleate in close enough proximity to each other, then they can actually overlap, and you can draw a space-time diagram that shows this possibility. Right?
And what happens if?
And in fact, in any bubble, since that bubble is going to be expanding outward at the speed of light indefinitely, right? So it just goes on forever, right?
Yeah.
That eventually it's going to hit some other bubble. Statistically speaking, that it's inevitable that there's going to be a bubble collision, but it can just be enormous spans of time.
So it almost has like what we might consider like a peculiar motion within the beer here, or
they're just the beer analogy breaks down because the beer is not expanding superluminally. But so in that sense, that analogy fails in this case. But you can show that these bubbles there will be collisions between these bubbles if they nucleate close enough to each other, because of the fact that you have essentially an infinite amount of time to do it. And short of drawing you a Penrose diagram, I'm struggling to come up with a good explanation for why.
If there's a finite space between them, and that space that stretches out at this inflationary speed.
Well, there's a scale there, though, right? So that essentially there's a scale at which things, even in an inflationary space-time, you have essentially the expansion rate as a constant, and that sets a length scale. So two things that are further apart than that length scale are moving apart from each other superluminally, but things that are closer to each other don't start out moving away from each other superluminally. Right. And so if you have two bubbles nucleated at a smaller length than that characteristic length scale, then they could in principle collide.
Okay.
Does that make sense?
Yeah, I think so. And we mentioned earlier how observers are trapped within their bubbles.
Right.
So what would the observers see in these bubbles as they...
The people who have studied this, the way they look for it is they look for sort of circular features in the CMB, so that these bubbles would intersect each other, and you would see features in the cosmic microwave background, for example, that would be signatures of these overlapping bubbles with each other.
So then there is causal contact. And
yeah.
Then, in principle,
in the case of a collision, there would be causal contact, and in principle, it could be observable if it happened in the past.
And in principle, traversable? Could you enter?
Yeah, I mean, the future state was these two bubbles would merge into a single universe. Then, yeah. That'd
be kind of wild to see. Yeah, I guess it makes me think of conformal cosmology a little bit, because in Penrose's, he's looking for the same kind of circles on the sky. Is that I'm guessing that's a different mechanism.
Yeah, the mechanism is very different in those cases. But
and there's no evidence for this in the CMB.
But no, there really isn't. Penrose claimed to find evidence, but anybody with any real expertise in cosmic microwave background pretty quickly debunked that claim.
So I guess that's a good alternative, because people might wonder about the alternatives to inflation, and there are these kind of cyclical universe type models like conformal cosmology. Maybe just explain what is the best alternative or alternatives to inflation.
Right. So you can create these sort of nearly scale invariant adiabatic perturbations that we see in the CMB. You can also create those under the correct circumstances in a collapsing universe. The hard part, of course, is then you have to have a bounce, and that bounce has to preserve all of these very nice symmetric properties of these things, and we don't know how to create bounces.
Oh, so if they're coming in together, then you're driving them all into causal contact, and then that memory preserves after the bounce.
And then the universe re-expands, and all of these things are still left over from the previous contracting phase.
Yeah, but you hit a singularity of...
The problem is that you have to, there's that old New Yorker cartoon where the guy's at the board and there's just like, and then a miracle happens, It's sort of like that, where you have the contracting phase and the expanding phase, and then what happens in between those two things is sort of like there's hand waving that goes on there. People come up with models to do it, but it's, in particular, if you have a flat geometry, if you have a flat universe, you can't go from it's forbidden in relativity to go from a contracting phase to an expanding phase. You can do it if you have like positive curvature and a cosmological constant that's just right. You can create these bounces and so on. The question of a cyclic universe, a truly cyclic universe, is a different one though, right? Which is multiple bounces that create some sort of steady state.
Oh, that's just a one-off then before.
So this bounce is a one-off, and you can create scale invariant perturbations in a one-off bounce. There are ways to do it. The key distinction is you wouldn't produce gravity waves, observable gravity waves.
So then you still have a singularity, but the singularity sits in the middle of your timeline.
That's right. Unless you, for example, or people who write theories down like this, they modify general relativity. So they come up with some sort of modified version of relativity that avoids the singularity. And, they get very baroque.
Okay.
And one of the problems that with contracting cosmologies in general is that when you look at perturbations in the universe, these little fluctuations in the density, in an expanding universe, you have two behaviors. There are two kinds of, essentially it's a differential equation. There are two solutions. One of them is called a decaying mode. So you create these perturbations and they decay away. And the other one is called a constant mode, where you have these things where they just freeze in and they don't evolve at all. It's called mode freezing, and it's characteristic of inflationary perturbations. Well, if you time reverse that, the constant mode time reverse stays constant, but the decaying mode now turns into a growing mode and you have instabilities. Right? So if I create tiny little fluctuations, the contraction makes them huge, right? And you have to sort of artificially suppress those in order for these models to work. And for me, this is one of the real shortcomings of them, is that it basically you have these inherent instabilities that happen in contracting universes that don't happen in expanding ones. But if you wanted to have a completely cyclic universe now, one where you had just repeating cycles and the universe basically goes through these things and then reconstitutes itself and resets its initial conditions and goes forward, there's been a lot of work on this, dating back all the way to like the 1930s. So there's a very famous paper by Pullman in the early 1930s, where he pointed out that the second law of thermodynamics ruins this, right? Suppose I had a universe that bounced and then bounced again and so on. Entropy always increases, right? The amount of disorder in the universe always increases. And this would happen in these cyclic universes. So each cycle would have more entropy than the last one. And he managed to do this very elegant proof that showed that if you had entropy increase in these universes, that these cycles couldn't go infinitely far back into the past. It's like a version of the BGV theorem where you had to have some sort of beginning, that you can't actually create a perfect cyclic system because of the fact that you're constantly producing entropy. And an easy way to see this is a universe like ours, right? Suppose we're in a bouncing universe, right? Well, we make all these black holes. When the universe recontracts, those black holes don't suddenly disappear. They all get crammed together. And when you get back down to that bounce, you're not going to have a smooth, homogeneous solution to the universe anymore. You're going to have a mess because of all this structure. Structure grows in a collapsing universe as well as in an expanding universe. And so you have to get rid of all this structure somehow in order to make this work.
Can you get rid of that with like enough time with heat death? You just evaporate away all the black holes?
Well, there are various proposals for this. Yeah. And there's an interesting one that Paul Steinhardt and Anna Iash proposed a few years ago, which was getting around Tolman's proof by using a little bit of inflation. So the idea would be that the universe bounces and comes back, and you create some entropy, you have star formation, you make black holes, you do all this stuff, right? You have to get rid of that. So what you do is you have a period of inflation that just empties everything out, dilutes that entropy down to a very low level, and then you bounce again. But you don't bounce all the way, but you don't pull everything back together again. You have this gentle bounce that keeps that entropy spread out, and they argue that you can create a perfectly cyclic universe this way. The fun part is that this BGV theorem that was applied to inflation actually applies to these as well, because the scale factor, the size of the universe grows from one cycle to the next in these guys. And you can actually use the same math that Borda, Guth, and Vilenkin used to show that inflation had to be past finite to show that this cyclic universe of Steinhardt and Iash also has to be past finite. So in fact, as soon as you start to use expansion to dilute away the entropy, you run into the other problem, which is that you have to the BGV theorem applies, and you have to have your geodesically incomplete.
Well, what is the story of entropy in eternal inflation? There is a initial singularity at some point from which this field emerges.
Or some kind of a boundary. We
so
don't
does
know
that
if
mean
it's singular, but
the entropy is has to start at some extreme point
Well,
there. And
the
just
inflationary space itself, right? When you're inflating, the universe has zero entropy, right? It's absolute
'Cause
zero
there's nothing in
temperature.
it.
It has nothing. It has nothing but the scalar field in it. That quantum mechanically, you're going to have a little bit, but I mean, classically, the entropy of this is zero, and that the entropy gets created later.
Is that, well, that's true in a per unit volume sense, but in
And
the,
that's what you care about, right? So how
Yeah.
much entropy is in your horizon?
because there's still, if you
Right.
had like a bazillion particles and they all smear out, yes, in any given volume, there's hardly anything, but those bazillion
Right.
particles are still countable. They're still out there, right?
Well, unless the whole thing in eternal inflation, that's infinite, right? And so now that there's no, as far as I'm aware, there's no particular prescription for calculating the entropy of an eternally inflating manifold. I don't think it's well defined. So the best you can do is talk about local entropy density.
Feels like a bit of a dodge, but I guess it does.
Yeah, well, we don't completely understand how entropy and gravity work, right? I mean, and this is really at the forefront of a lot of quantum gravity studies now. So the fact that the entropy of gravitating systems appears to scale with the area of the system rather than the volume as it does in normal thermodynamic systems is really weird. And I think, once again, I'm just a silly cosmologist, but I think that we're still trying to grapple with what that means altogether. And I don't think that we really understand why gravitational entropy works the way it does.
So I wanted to finish maybe by talking about the limits of science a little bit, and the singularity in, even before inflationary theory came along, was always a big problem, and it's always bothered people, and that's why people often turn to a creator or something at that point and say, okay, God did it, that God created the Big Bang. And inflation neatly kind of gets rid of that and says, actually, no, there's a phase before that. We can explain what happened before that. And that's kind of the story of science, is, what makes the sunrise and the sunset. And at one point we said God did it, and then we came up with, actually, no, it's caused by X, Y, and Z, caused by Keplerian orbits and the rotation of the Earth. So you can come up with these explanations, but eventually we still, despite our best efforts, seem to hit a singularity. And you mentioned that there may be something which generated, presumably there was something that generated this inflationary field.
Some sort of weird pre-inflationary state that we have like no idea what it could have been like. Yeah.
And that seems completely inaccessible, even in principle, to the tools of science. And so I guess if you were to look in the crystal ball and project the future of cosmology, presuming we don't destroy ourselves in like hundreds, thousands of years' time, it feels like there's going to be a certain limit as to how far we can go. And that certainly feels like a hard limit. And
another one of these in principle, physical limits to what we can know, what we can learn about the universe. Yeah.
And if that's true, then does that not also mean we've almost hit the end of the theoretical road already? Like there's not, where do we go from here? If we've already hit this, inflation theory to me almost feels like a meta theory already. It's almost a bit abstract, sits outside of the universe. And so to have another level of abstraction above that is completely untouchable.
Right.
So is this...
We could, I mean, it's a reasonable thing to think that maybe we could identify the quantum field responsible for inflation, just like we've identified the existence of the Higgs boson. That's one of those things that's perhaps in a practical sense undoable, but in principle, there's no reason why we couldn't actually say, oh, we've identified the field that drove inflation.
Yeah. So we find the particle.
We find the particle,
yeah, okay.
Right? Yeah, there would be a particle associated with it, presumably some really heavy scalar field like the Higgs boson or some cousin of the Higgs. That could happen. I mean, it might not happen for a long time, but it could.
And could that particle encode anything about what came before it?
Well, that's the thing. Suppose we found that particle. What would we learn about the pre-inflationary phase from studying that particle? I don't know. It may be that we could come up with some kind of indirect knowledge if we actually could take this field that did this thing in the early universe and manipulate it and study it. I don't think that's beyond the pale of possibility.
I guess I'm thinking a little bit of Richard Feynman, and he once said famously that, he doesn't really have a hunch as to what the universe really is. It may be that there's some single elegant thing which wraps everything up really neatly, or it may be like an onion where you peel back a layer and there's just another layer and another layer, and it just goes on forever like that. And it feels a little unsatisfying. I think a lot of theorists really hope it's the former. It's kind of frustrating if it's the latter, because you'll never obtain truth. You'll never really know what the answer is.
Yeah.
But philosophically, do you think that's probably closer to the answer? It seems that way with this pre-inflationary phase. It kind of lives in that onion sort of mode.
I think this is one of those cases where even if you had the field, even if you said this is the inflaton, what property of the universe would have given rise to this, sort of this pre-inflationary state? That's another question altogether, and I think that one would be much, much more difficult to get. And then, what if even if you came up with a good model for that, we identify the inflaton and we say, oh, okay, here's this sort of pre-inflationary state, and we can construct it and we can understand a particle theory for it. Is that going to end up being complete, or is there some larger theory that you need to explain that, and so on and so
right.
and so we've hit this one boundary, and even if we could, in the amazing thought that we could, even if it turned out we could push beyond that boundary, is there going to be just another one waiting for us on the other side of it? Is one of those tough questions, right?
I guess I'm reminded, you said, it could be that we were born in a future universe where cosmology wasn't possible, because all the galaxy clusters would have receded beyond a horizon, and they would never be able to even get as far as we have. And it may be thus that we just have to accept that there are certain things like that, and this is a horizon for us. This is at the point we can't see beyond.
Well, and we certainly, have these examples of physical theories that tell us that there are certain things that we can't know. And so the inflationary multiverse is an example of this. The pre-inflationary state very likely is such an example.
Yeah.
The limitations of quantum mechanics are another example that I can think of. Right.
Right. And so that's not a weakness of the theory. That's just
it appears to be a feature of reality that we have to, as scientists, we have to come to terms with. And I don't know how to do that in a way that, makes me happy. And I think this is one of the reasons why people try so hard to come up with things like cyclic universes that are infinite to the past, because they allow you to dodge that question.
Yeah, have continuity. Right? Yeah.
And so if the universe just goes back in time forever, you don't have to answer the question, Aristotle's question of the first mover. Bruno, right? When I was writing this book, I was reading Bruno. And this was a question that he was very, very concerned with. And in particular, if you take Bruno's Copernican conception, right? So he's like, okay, there's all these other worlds. There are, and he put theology into it, how many of these worlds had been saved from sin, and so on. But it also raised the question of where exactly do you put God? Right? Because in the old Ptolemaic view of the universe, you had these spheres, and beyond the outer layer of the sphere, that's like physically where heaven was, right? And so there was this Empyrean realm that was outside of the universe, that was the habitat of these spiritual creatures, right? Bruno quite astutely realized that if you accept Copernicanism, that you have no place to put that place, right? And a lot of his work was concerned with this, and his solution was a Copernican one. He borrowed a lot. He borrowed a lot from the Epicureans and the ancient atomists, the people who believed in the existence of atoms. And so Bruno's philosophical answer to this, which was a very Copernican one, was that God actually lived in the foundations of of physics, essentially, in the foundations of the universe, that he lived inside the atoms.
He was embedded.
He was eminent rather than immanent in the universe. And so he came up with a Copernican solution to the problem of where you put God, that I think is very similar to looking at these, so how the universe just dissolves into uncertainty at very small scales, is that the answer to that question, the boundary condition that you have either at the beginning of the universe or at the smallest scales of space and time, is one where the universe itself kind of dissolves and is in a sense self-answering. So Bruno's answer to Aristotle's question of who was the first mover in the universe, the ultimate cause, is that the ultimate cause is diffused into the foundations of the structure of the world itself, and the question really ceased to have any meaning. And I think that is a lesson that physicists are still rediscovering. And this is one of the reasons I'm so fond of Bruno's philosophy, because he grappled with this in a very prescient way, and one that presaged a lot of these questions that we are now having to cope with as modern scientists.
Well, for these questions, and to go much deeper, it sounds like we've gone very deep in today's conversation, inflation, but this book goes much deeper than we've talked about today. So I want to recommend folks check out this book for much more detail. And where can they learn about your work? Well, where can they find you?
I'm on Twitter a lot, or X, I guess it is now.
Yeah.
The book is available at bookstores, Amazon. It's easy to come by. And as we talked about beforehand, I'm working on another book, which is a technical treatment of the same subject. So this is this book, except with all of the technical details included in it. And I'm in the process of writing that now. It should be out probably next year.
A much needed book. So I look forward to seeing that.
So
thank you for your time, Will.
Thank you so much for having me. This is a great conversation.
This is great. It. Yeah, thanks. So that was my conversation with Will Kinney. I hope you enjoyed it as much as I did. And if you did, you should really check out this book. An Infinity of Worlds is available at all good book retailers and Amazon, etc. So please do check that out. You know, inflation is one of those topics that really skirts the line, right, between being on the precarious edge of almost being non-scientific. It makes some predictions about the existence of other universes, an infinite number of other universes, which are obviously untestable and seem so, I don't know what, woo-woo? Like, what's the right word? Like, kind of out there, that it's easy to dismiss it and say, okay, this is obviously kind of a crackpot theory. But on the other hand, it makes predictions about things happening in our own universe, such as the superhorizon scale seen in the cosmic microwave background and the gravitational perturbations that we might want to detect with gravitational wave detectors that are manifestly experimental and verifiable. In fact, one of them has already been verified. So in that sense, it's hard science. And so it is a really interesting theory that seems to have its foot in both worlds, right? The foot in the world of hard science, and also its foot in the world of this kind of multiverse stuff that a lot of people get deeply uncomfortable about calling real science. So it's a wonderful idea. I think it's important that we all get our head around it. And quite frankly, we just don't really have any good alternatives to explain so many properties, the flatness of space, for instance, without invoking inflation. So it does a wonderful job of explaining so much about our universe, but science is always in the process of hunting for greater truth, hunting for deeper truths, and so perhaps one day an experiment will come along that proves that inflation is somehow wrong, or maybe we'll verify it's true by getting those gravitational wave observations in the future. I think that's what makes this field so exciting, that there's so much we don't know, but we can think of ways, at least in inflation, of actually being able to make progress, actually be able to learn more by building these new experiments. So I hope you enjoyed this. If you like these conversations, you want to hear more about cosmology, exoplanets, life in the universe, and maybe even inflation down the road, we could do some more episodes on that as well, then you should support what we do. Right, so one way is just to share and like these podcasts. Please make sure you're subscribed. But if you want to become a super fan and really help us out, the best way to do that is head to our website. That is thecoolworldslab.com/support. So coolworldslab.com/support. Head over there. There's a whole bunch of membership tiers, anywhere up from the price of a coffee per month and up. And if you do that, you are supporting not actually directly the podcast or the YouTube channel, but really you are supporting my research team. So that money goes to astronomy research. And by doing that, it means it frees me up. I have to write less grant proposals, things like this. And so I can make more of these episodes, have more of these conversations. That's the best way to help us out. coolworldslab.com/support. So thanks for watching. And as always, I will see you in the next episode. So please stay thoughtful and stay curious.